right, it's an international atmosphere in this room, so we are so happy to welcome all the friends from across the world to join this event. Now, welcome you to join the 2024 Net Zero Tech International Contest at Taiwan, hosted by the TECO, Technology Foundation and National Taiwan University. At this moment, I would like to join with you to welcome the judges, which is a very important figure of the day to come into our stadium. So first, I would like to announce the judges for the main contest judges. 我们现在先邀请我们评审委员入会场。首先，我们欢迎是主竞赛的评审委员何坤耀 ，Welcome， 谭俊松、周志宏、陈成亮、李宗明、林法正。Those are the judges for the main contest. Now followed by the international contest judges. 现在是国际赛的评审委员金光恩、童千祥、蒋本基、陈志成、赖延生、高志明。而最后我们要邀请的是林一平评审委员、苏方静评审委员。以及竞赛总召集人台湾大学陈文章校长 ，the convener of the competition, president of the National Taiwan University 陈文章 ，welcome, welcome. Right， 我们今年的赛事总共分为主竞赛以及国际赛，并且在今天早上9点10分会两竞赛同时展开。为了扩大团队之间的交流以及各议题之间的交锋，主竞赛跟国际赛的赛区呢？简报以及所有的实作都可以开放各界参观，各位也可以相互的聆听、讨论、合影留念，以达到广结善缘、多交朋友的目的。Now, the year's event is divided into the main category and international category, which will be held simultaneously starting from the 9:10 this morning. So in order to expand the communication between the teams and the crosstalk between the topics, now, all of you are encouraged to listen to each discussion and the presentation and also take photos, not just for the competition and the winning, but also for cooperation and the international friendships. 那么现在呢，我将会依照我们荧光幕上面的 PPT 来为各位介绍一下我们今天要一些重要的注意事项。Now, I would like to show you on the screen to how is the general idea at a glance about our competition. Now, this is organized by the National Taiwan University and the TECO, Technology Foundation. Now, these two very high-tech institutions in Taiwan, they focus on the technology development and the talent cultivation. 这是在国内呢非常重科技人才的发展以及深耕议题的重要两个单位，一个是学术机构，一个是民间基金会。Now, the advisory committee including the Ministry from Education, Environment, National Science and Technology Council, and Ministry of Economic Affairs. Now, most of them are governmental agencies. They're working together, also want to push this one and make all things happen successfully. And the organizer, including the several organizations right over here, that's very wonderful. And sponsorship, that's what the focus, how to make a contest better and better each year, because we have good sponsor and endorsement for several enterprises in Taiwan and also the academic institute. Those are very high, prestigious enterprise in Taiwan, so appreciate it very, very much. Now, they also, their supervisor and the head also will present this afternoon in the awarding ceremony to present the award for the winning team. Now, these are the logos, so very colorful, right? So thanks to them. Under the leadership of the convener of this competition, I think the most endeavor was put inside from the National Taiwan University, especially many thanks to the president of the NTU. Now, right here is the very great stadium of the National Taiwan University. We use these very great facilities and the venue to hold this competition. And all of the things will be conducted under the leadership of the President Chen Wen-zhang, and we have several themes. The theme is about net zero technology, echo to the UN about 2015 vision, and there are 6 topics， 有6个主题呢在这边展开。 including the renewable energy, negative carbon, how to reduce it, and the electric vehicle, and etc. Those are 6 topics I believe you all of you understand. 我相信各位都已经知道，因为你们已经选好你们的作品题目了嘛啊 ，you already selected topics of your work. Right here, at a glance, this time we increase the amount and the momentum of the entire competition. 有来自99队国际赛的竞赛报名，141队来自主竞赛报名，总共是来自13个国家，有240个队，人数报名呢就有998人。那么我们精选了2个类别，各20队，所以有40个队伍进入到今天的决赛 ，so in total 40。那么今天呢，出席我们有统计了一下，大概114人参加国际赛，主竞赛有120人。Now this is a very great achievement. We have an increased number, not just for the individuals, but also for the team, starting from several years ago. Because 2024 is a very good year that we will restart our competition. And in the final today, there are 14 teams, 20 in the main category, and then another 20 in international category. That is the great. Let's see what happened today about your performance, right? And especially for the international team, we do have sponsorship and subsidies for international team to increase their willingness to join because they have to fly from their own country to Taiwan. But during your stay in Taiwan, not just for competition, I hope you can stay longer and go to our CBD to see, and also you can shop if you like. Spend some money right over here. Thank you very much. Now, they are also have the awards for you. Depends on the different the places that you won. So they would be announced and represent the trophy and the bonus this afternoon, right? And this is the total number. If you can mark, we have a great number right over here. It's 99, 8 individual enrolled, but finally we have 866 come into the entry of the judgment, right? That's the achievement of today. Based on the jury's committee, we set 4 criteria for evaluating your work, including the first one, the problem solving and technical value accounts for 40%, and creativity accounts for 25%, technical content and feasibility account for 25%, and last, completeness of the project accounts for 10%. And all 100% we evaluate based on your work and your presentation. Now, this is all the sponsors that set up all their awards and their prizes, though these are a lot of names there, so we appreciate it very much. And the good news is this year we set a very special award we call the Best Popularity Award. So all of you, not just for the competitors, also from your friends, you can have time to get 6 tickets from our service desk. During the day, you can put your ticket number and also name your favorable team on the ticket, put it in the lottery box, and in the end of the ceremony, we will announce the winner. Two teams will be selected as the Best Popularity Award. And for those who put your vote inside, also have 1 chance to win the 65-inch big television sponsored by the Dongyuan Group. That was wonderful. I like the 65-inch big TV, right? Okay. So I will announce it many times during our break. So don't forget your right to join this lottery drawing. 请各位呢在不同的时间点可以随时去选择你喜欢的团队，然后投下您的票。会有2个团队呢获得这个最佳人气奖，而且投票的朋友们呢，你也可以从我们的等下下午我们的长官抽起来，有1位可以获得65寸的东元大电视啊，最棒的啊。Now about the entire agenda of the day, this is the glance. We can now currently in the morning we do the briefing, and then we have an entire competition, and in the end we have an awarding ceremony in the afternoon. And during the time, you can also have a time to rest, to interact with your friends. Today, in the international competition, I will be the MC for all the process. And in terms of the main competition, on the back side of the auditorium, now another host, 校长，区德恩校 ，Where are you? Right over here. For 主竞赛的呢，请看一下您右手边这位区校长，然后 he will play the role to help you to process in the entire competition. 这是负责主竞赛的主持人，是我们的区校长，区德恩区校长。So 非常感谢有机会为各位服务。Now there are some important figure here. You already signed up, so based on the team number, that is the order that you on the stage to present. And you have to confirm everything before your demonstration. For the international, there are in total 12 minutes, but in the first 6 minutes, you will be on the stage to present your work by your PPT and the video. And another 6 minutes we will accompany with you, go to your booth and see how you operate all the process. And judges will come to your booth as well, and Q&A and will also be conducted over there. 就是在国际赛的部分呢，主舞台区有6分钟的时间轮流进行简报，每一次是6组，6组结束之后呢，会带到您的展位进行您的实际操作。评审委员在那时候呢，也会随您跟去您的摊位，然后 team 以及进行所有的问答时间。这是国际赛的部分。那我们也会有计时器，反正在1分钟之前呢，我们会响铃一响。我们请我们大会工作人员示范的是，so 1 minute before the completion, so ring 1 time, yes. 当时间停止的时间抵达时候 ，when the time is up, there are 2 sounds. Okay, heard that? 就会提醒你 ，if you will not stop, I will say something to thank you. Okay. All right, so that's the rule for international and the main category. Another notice right here, you have to stand by in front of your booth or in the area, for example, over here, 10 minutes before, 15 minutes before your presentation on the stage. 15分钟之前，在这个地方国际赛15分钟前要先预备好。那么如果是主竞赛的话呢，在您的展位上面的10分钟前要准备好，这样我们评审移动哦才会比较尽快就进入到你的实作状态。那么在评审移动的部分是不计算时间的，计算时间时从你开始讲第一个字开始，各位评审大家好的那个时候我们开始计时。So the movement of the judges will not, the time of the judges' movement will not be timed. Okay, the time will starting from your first word out from your mouth. All right? 在这个过程当中呢，我们指导教授可以发言跟补充，但是尽量让同学们来回答。如果你前一年已经有得奖的话呢，又是同一个作品，那么您可以比较一下去年跟今年的差异或一些更精进改善的地方。For those judges and instructor, for the judges or the leaders, you can also add some comments for your team. But let your student handle the part Q&A as many as possible. If your team has won any award last year, please compare to what you have each year, and then we can see how to improve and make your work shining better. Okay. Every team will take turns based on the number of your team number, and that's the way we will remind you about the timing. Okay. The total, there are for 20 teams in each category, the top 7 will be chosen, and different bonus will be given. And for extra, number 8 to number 20, they also have the Excellence Award, will be awarded by 50,000 NT dollars. 就算你是佳作的话，也有5万块钱的奖金哦。那其他7个名次呢 ，Top 7前7名呢有不同的奖金，而且是由不同的设奖单位来提供，所以我们非常感谢。Again, many thanks to those sponsors. All right, the jury, there are different categories. I already introduced you, so I will skip this moment. It's the judges. And finally, once again, we have to thank the President Chen Wen-zhang to provide a great facility and handle the whole thing together and make it happen. So once again, big applause to our President of National Taiwan University, Dr. Chen Wen-zhang. So this is the housekeeping item. We have set a round table in the back of the area. You can eat, you can drink, And don't forget to take many photos for you to maintain your friendship. Any questions, if you have, please go to the service desk to ask our staff. Okay, so far, do you have any question about our orientation? Good. So now time is 9:04, starting from 9:10, which 60 minutes away from now, we are simultaneously will go start on the main category and the international category. So at this moment, I would like to invite all of the competitive team for the main category. Please move to your booth. 现在请我们主竞赛的团队呢，可以到你的摊展位上面进行准备。For international category, you stay right over here, and the judges also on your position. 我们的主竞赛的团队、主竞赛的评审委员呢，也可以往我们后方休息区移动。那么可以先招手，在我们主持人的引导之下，再从第一组9点10分正式开始。For international judges， 我们国际赛的评审也请到前方，我们帮您准备好的区域呢入座。And for the international teams, are you ready for the team number 1 for international category? You will be the first on the stage, so please prepare. 好，我们现在就准备，还有大概4分钟时间，我们会即将同时展开。第一组上台的国际赛的团队呢，您将是第一个要去做准备了，所以你现在可以进行您的简报档，最后再测试一下是否运转的顺畅。那么第二个团队呢，你是下一个，所以您其实也要 stand by 了 ，all right？ OK，Thank you very much。我们再过5分钟之后会正式的2组同时展开，谢谢大家 ，Thank you very much。Wish you a good, successful day. Yes， 严格 ，OK。The judges mentioned we will control the time strictly, OK, very carefully. 好，现在是9点9分，再过30秒呢，我们双边会同时开始。好，曲老师、曲校长。我们现在是9点10分，所以现在我们主竞赛以及国际赛区的竞赛呢，即将同时开始。Are you ready? All right, 5, 4, 3, 2, 1. Let's start. Let's welcome in the international competition. Let's welcome the team number 1.
Okay, good morning, everyone. It is my honor to be here to share our research. My name is Chen Zhale, a member of Professor Zhahardin's team come from National Taiwan Normal University. And today's topic will start from the superhydrophobic meta-organic framework sponge composites for oil water separation. Here my outline, the problem that our homeland is facing. We know that marine environment is crucial for human survival, yet it faces severe stress from the chemical pollutants, such as the persistent organic pollutants, heavy metals, emerging contaminants, and nutrients. And in the oil pollutants, oil spills are a direct marine pollution of it, and improper handling can lead to the soil and water contamination. So here, the 17th Sustainability Development Goals have announced in 2015, include 6 aimed at environmental and energy sustainability to show the importance of marine and water resource protection. So next, I would like to introduce a material, meta-organic framework. Meta-organic framework are porous solid materials synthesized by the metal iron and cluster with the organic linkers. Due to its large surface area and to novel porosity and highly functionalization, it already applied in different types of applications such as the separation, absorption, and catalyst. So in result and discussion, The first part of our research, we have used a lattice rearrangement morph system to construct a superhydrophobic morph. And how we did it? First, the defective ALTD53 was modified with the alkyl trans using a click reduction, and then followed by the internal rearrangement during the activation to achieve the high porosity and high crystallinity. Next part, for application in the oil and water separation, we have modified the melamine sponge, and then the superhydrophobic ALTZ 68C18 was conveniently immobilized onto the sponge to form the superhydrophobic sponge. So from the images, we can see the superhydrophobic sponge shows excellent hydrophobicity compared to the original sponge. And it also shows the great adsorption capacities of a large board of the solvent uptake and oil uptakes. And its good recoverability and the recyclability of these materials also achieved during the adsorption and desorption of the inhabitant 10 times. And from the SEN images, we can also see the sponge have successfully coordinated on, the morphs have successfully coordinated on our sponge. So here I will present you a video showcasing the application of our sponge. So we can first we use the pump oil. We squeeze the pump oil with the seawater and just put the sponge inside. It's just in a few seconds we can successfully to remove the pump oil. And next part, we also use the crude oil mixed with the seawater. We can see the sponge can very rapidly to remove the crude oil. Okay, conclusion part. So for the future application in industry, we also have built a squeeze drawer machine. And this squeeze drawer machine is easily can use the scale up the sponge to squeeze the crude oil out and then bottom the holder. This holder we can to collect the crude oil and for next application. So the usability of this material can reduce the cleanup cost and material waste. And this material is totally environmentally friendly. And this portability make it a rapid response tool for various emergency applications. So in the end, I want to share a sentence from the Dr. Sylvia Earth. No water, no life, no blue, no green. Thank you for your attention.
Well, thank you very much. Thank you. Now we are moving on to the team number 2 for international category. You ready? Okay, you can start.
Check.
Hello, good morning everyone. So this is our project related with the next generation energy systems. So we are 2 universities competing in this project. One is Taikada and another is NTNU. So these are the outlines of our presentation. The first is introduction, and the second one is structure of the proposed converter, and third one is the proposed maximum power point tracking, and another is simulation and hardware, and the next one is energy benefits, innovation, market potential, and technical characteristics, and then it is applications and conclusions. So this is the introduction of our presentation. The global warming is predominantly caused by greenhouse gases. So in order to reduce the greenhouse gases, we have to switch to renewable energy sources. So like solar and wind energy. But the problem with the renewable energy sources is that we have lower voltage levels. But in our day-to-day life, we have to boost the voltage levels of these renewable sources. So there is necessity for boosting up the voltage. So in order to boost up, we have to use the DC-DC converters. So there are issues with the conventional converters, like the boost converter and quadratic boost converter. So these converters have one problem is like they give us higher boosts but at higher duty cycle. So at higher duty cycle, the problem is that there are losses. There are conduction losses, there are parasitics losses, there are thermal losses. So in order to enhance that, our team has introduced a novel high gain converter. So this is our novel high gain converter. So it has 2 inductors and 6 capacitors and 7 diodes. So the gain of the converter is 4 times of the quadratic boost converter. So the advantage of the proposed topology are like higher voltage gains at lower duty cycle. So there is only one switch, so it is easy to control the switch, reduced voltage across the switch. Like in our proposed circuit, we get reduced voltage across the switch. And there is common ground between source and load. So these are the modes of operation of our converter. So there are 2 modes of operation of our converter. The first mode is like there are 2, actually the circuit is 2-level cascading circuit. So one level boosts up the voltage and another level again boosts up the voltage. So at output we get nearly 10x voltage. So these are design concentrations. So these are the capacitor equations, inductor equations, and these are the voltage triggers across the switch and diodes. So this is the important part of the project. This is the inductor design. So in order to successfully achieve the higher efficiency, so it is necessary to design the inductor because there are two modes of operations in the DC-DC converter. So, there is DCM and CCM. So in order to design, so we operated the converter in the CCM mode. So another part of the project is like we use maximum power point tracking. So for maximum power point tracking, we use 5 points. So these 5 points, like when there is shading and there is cloud or there is light. So they pile up on a single point in order to give us the maximum power at output. So this is the hardware setup of our converter. We have tested our converter in NT, NU, and NTUST labs. So we have also tested in MATLAB and PSIM. So this is the hardware board of our circuit. You can see this is the table of our specifications of the hardware. So these are the waveforms of the converter. The left one is the simulation waveform, and the right one is the experimental waveform. The waveforms are at 35 volts and the 40% of duty cycle. This is another waveform at 32% of duty and 45 input, and the output voltage is 381. So this is another waveform. So this is the MPPT waveform. So in this waveform, what we did is we choose the maximum power point. So in order to boost up the voltage level.
So here are the advantages of our converter. It saves the energy and also it maximizes the efficiency. So you can see by applying the MPPT technique, the efficiency of the converter achieves up to 99%, and also it gives the very low cost. So these are the applications of our converter. And for the conclusion, we see that the high bandwidth converter achieves up to 96% of the efficiency at 192 watt. And also the cost is very low, which is the 700 NTD. And also efficiency, when we see we can apply the Converter, thank you.
Thank you very much.
Thank you very much, sorry.
This is the team number 2. All right.
Microphone check.
Then I will follow by the team number 3 of the international categories.
Hi everyone, we are Group 3 from National Taiwan University. Today, I would like to introduce you with an advanced carbon capture and elimination process technology using membrane engineering, which is known as AcceptMe. Can you imagine Earth with more extreme weathers such as droughts, flood, global warming, and typhoons? Climate change has become more serious each year, driven by the rise of atmospheric greenhouse gas emission. For instance, solely in 2022, Taiwan has recorded a greenhouse gas emission of around 285,000 kilotons of carbon dioxide equivalent, in which 91% originated from the energy sector. Energy has become the living essentials for humans. With the increase in human population and industrial revolution, we can see from the breakdown of energy sector for production and utilization, almost 63% of the emission originated from the power plants when generating energy. In 2022, about 80% of the total energy is generated using natural gas and coal, which produces large amount of carbon dioxide during the combustion process. Conventionally, amine-based absorption is the most commonly used carbon capture technology now, in which it primarily works on adsorption and desorption of carbon dioxide using amine solution. Although amine-based absorption is effective, however, it consumes large amount of electricity, costs, being hazardous, and most importantly, it brings negative impacts towards the environment. Hence, in order to tackle this problem, to achieve net zero emission, are you thinking that our solution will be space-consuming and complex? No, instead, we are proposing the use of membrane engineering technology, which is compact yet efficient for carbon capture to tackle. From the technology evolution, initially amine-based absorption has played an important role. However, in recent decades, the focus has shifted towards membrane adsorption and membrane separation. Today, we would like to propose you AcceptMe as a hybrid technology which composed of both membrane adsorption and membrane separation that works simultaneously to tackle the net zero emission. In AcceptMe, the membrane adsorption allows carbon dioxide to effectively adsorb onto the membrane surface and release when heated up. As you can see here, the carbon dioxide will first adsorb onto the membrane surface and release when the hot vapor passes through the carbon tubes. This will allow us to obtain a concentrated carbon dioxide. And this cycle will continue to be operated as we can actually put cold water into it. Next, the purified carbon dioxide will then pass through membrane separation to be further concentrated, as shown in this video here. As you can see here, the 50% concentrated carbon dioxide will then be separated and move towards the hollow fiber tubes, and while the nitrogen is barred from entering the membranes to allow us to obtain a concentrated carbon dioxide. The core technology of AcceptMe involves the use of metal organic framework, MOF, as one of our effective materials, and it possesses high selectivity towards carbon dioxide. Moreover, with the use of hundreds of hollow fiber membrane packed within a closed module, more carbon dioxide can be treated within the same time frame. Most importantly, AcceptMe is a hybrid membrane technology which involves the use of both membrane adsorption and membrane separation to work simultaneously to overcome the limitation of conventional technology, as we can produce high concentration of carbon dioxide at a lower energy and cost consumption. Moving on to the experimental results, we can see that when MOF UTS-616 is coated onto the copper tubes packed within the tubular module, we can achieve a high packing density for the absorption process. As our Moreover, our module has showed a higher absorption capacity towards carbon dioxide than nitrogen. Moreover, having a good long-term stability, as well as having a promising purification effects towards the carbon dioxide, as the concentration of carbon dioxide can be increased from 11% to 50%. The concentrated carbon dioxide will then passes through a hollow fiber mixed matrix membrane composed of MOF 808. In the membrane separation process, hundreds of membranes are actually packed together and to separate the carbon dioxide. Herein, it allows us to enhance the results as the carbon dioxide purity can be further enhanced to 99%. With the innovative AcceptMe technology, we have confidence to becoming the potential alternative for carbon dioxide capture, as we use membrane engineering to allow us to improve the carbon dioxide capture rate by 50% while using a smaller equipment at a lower energy and cost consumption. Moreover, AcceptMe aligns us with different SDG goals such as 7, 9, 11, 12, and 13. Hence, don't hesitate to accept me to accept a carbon-free tomorrow. Thank you.
Thank you. Thank you, team number 3. Just right on time. Now followed by the team number 4 of the international category.
Check. Hi. Good morning, everyone. We are international competition team number 4. Our title is low-cost energy efficient atmospheric plasma jet process, nickel cobalt metal organic framework, electric catalyst in anion exchanging membrane water electrolysis module. We are a joint research team from National Taiwan University and National Taiwan University of Science and Technology. Renewable energy has intermittency issue. It is necessary to overcome the intermittency issue associated with renewable energy source. Access to renewable energy can be used to produce hydrogen through electrolysis for energy storage without carbon emission. And the application of hydrogen are versatile. There are 3 types of water electrolysis technology. The first is alkaline water electrolysis, AWE. The second is proton exchanging membrane water electrolysis, PEMWE. And the third is anion exchanging membrane water electrolysis, AEMWE. AEMWE is the focus of our research. AWE can be operated in alkaline environment without requiring noble metals. And PEMWE can produce high-purity hydrogen. And AEMWE combine the advantage of AWE and the PEMWE to produce high-purity hydrogen without noble metals. However, the higher potential of OER limits the development of AEMWE. Therefore, improving the activity and the durability of electric catalyst is crucial for development of AEMWE. We use solar cell method to grow nickel cobalt MOF on carbon paper for anode of AEMWE cell. Atmospheric pressure plasma jet, APJ, is used for post-treatment on nickel cobalt MOF. And this is our APJ equipment. APJ treatment can simultaneously improve the performance and durability of AEMWE. Through APJ treatment, the hydrophilicity and OER activity of catalysts are improved to enhance AEMWE cell performance. And high temperature post-treatment can enhance catalyst durability, and APJ can rapidly achieve 500 degrees Celsius in 2 seconds, enabling a fast processor method. And APJ operate without vacuum system, offering low cost and energy saving, and can replace energy intensive and lengthy furnace calcination process. In the AEMWE cell, we use nickel cobalt MOF as an anode. Once the AEMWE cell is connected to the system, inject an electrolyte and apply voltage to start hydrogen production. And the oxygen is produced at the anode, and hydrogen is produced at the cathode. APJ treatment improve the AEMWE performance and lower the energy consumption for hydrogen production. Plasma treatment reduces the voltage required at the same current density. Low voltage requirement can reduce the energy consumption for hydrogen production. With 60-second APG treatment, the energy consumption reduced to 48.9 kilowatt per kilogram at operation current density of 500 milliampere per centimeter square. Our research is compared with a commercial AENW stack electrolyzer from German company Injector. The energy consumption is 53.76 kilowatt per kilogram from Injector system, and our energy consumption is 48.9 kilowatt per kilogram, is lower. APJ can be applied without vacuum system. It is therefore low cost, energy saving, rapid precision technique. And CCR long-term testing show that 60-second APJ treatment enhance the durability of electrocatalysts. The AENWE degradation rate decreased from 718.3 to minus 118.3 microvolt per hour. In the conclusion, APJ treatment for electric catalysts is an energy efficient, low cost, and ultra fast process. It achieves this through two key features of APJ: no need for vacuum operation and the ability of rapid thermal annealing. Furthermore, after APJ treatment, the anode electric catalyst can simultaneously improve the performance and durability of ANWE. So using APJ offers a promising solution to OER limitation in ANWE. Thank you for listening.
Thank you very much, team number 5. Team number 4. Now we're going to move on to the team number 5.
Mic check. Wait.
Hello, distinguished committee members, teachers, and friends. Today, we are team number 5. Today, I will introduce integrating a novel coastal wave energy converter, CWEC, and carbon negative cement for net zero. Here is our outline. After introduce our team members, we will explain our motivation for designing CWEC. In project overview, we will present our system, and finally, we will discuss the various benefits our system can achieve. We are a team comprised of individuals from diverse fields. Our motivation stems from Ocean Energy Europe's prediction that wave energy has great development potential. Taiwan, rich in ocean energy, targets 1 megawatt marine energy capacity in 2030. Our project aims to harness this potential, advancing Taiwan's energy transformation and supporting global renewable energy goals. Our project integrates 3 major parts: coastal wave energy converter, CWEC, flywheel energy storage system, FESS, and carbon negative cement. The CWEC consists of 6 parts: generator, hydroturbine, blade, base, support, and carbon negative channel. The power generation process starts from collecting waves, push the blades, and spin the hydroturbine, allows the generator to produce power. After several experiments, we found that a 90 centimeter channel length and 30-degree angles creates the most amount of power. And there is a huge difference between our system and oscillating water column, OWC. CWEC boosts efficiency by decrease the energy transformation stage. Since wave energy is intermittent, so we use FESS to store energy. FESS uses a rotating flywheel and motor generator to convert electrical energy to mechanical energy. FESS stores energy by speeding up the flywheel, releases by slowing down. Compared to lithium battery, FESS quickly charge and discharge, more safety, longer lifespan, and lower pollution come in handy to our system. Our strategy ensures the CWEC's power outputs meet the grid standard while keep the flywheel state of charge within safe limits. When wave energy is in generating cycle and generated power meets the grid standard, allow the flywheel to speed up and storage energy. When generated power exceeds the storage limits, the system will enter residual power mode with potential for future hydrogen production. Furthermore, if the generated power doesn't meet the grid code, the flywheel slows down to release energy. And the flywheel also slows down to release energy when the turbine isn't generating power. We optimize the flywheel size by minimizing the loss of power supply probability during simulation. The carbon-active cement can absorb carbon by using 30% of biochar. Additionally, it's waterproof and boosts durability and 3D printability. Due to CWEC's simple structure, constructing a CWEC uses 40% less cement and 17% less gravel than traditional OWC. The carbon footprint of CWEC is significantly lower than traditional OWC, from 21 tons to minus 4.5 tons carbon emission. Taiwan's coastline has a 10,000 megawatt potential wave energy. By deploying CWEC, the carbon absorption can be equivalent to 2,800 Da'an Forest Park. Taiwan has a 10,000 wave potential energy, and developing just 0.1% could create green energy benefits worth 4.39 billion NTD. There are 2 million tons of wave dissipating blocks in Taiwan. If we replace them with carbon-active cement, 1.8 million carbon will be absorbed, and it equals to 4.5 billion NTD. Additionally, CWEC could serve as artistic installation, artificial reefs, boosting biodiversity and advancing SDGs goals. In conclusion, our CWEC system achieves a multi-win situation in net zero and biodiversity. Looking forward to creating a prosperous future. Thanks for your listening.
Thank you. Thank you, team number 5. Now, moving on, we are going to the team number 6. At this section, after the team number 6, we're going to move on to their booth to see their work and demonstration.
Check.
Hello guys, we are team number 6 from National Taiwan University. Now I'm gonna take you guys to see what green and advanced magnesium-based hydrogen storage alloy is. So our technology focuses on 3 key highlights. Number 1, hydrogen storage capability exceeding 5.5 to 6.5%. And then high cycle storage at operating temperatures below 300 Celsius degrees. And safe and long storage duration at room temperature. So why do we need to improve the storage methods for hydrogen energy? Because we want a more efficient storage. The alloys allows hydrogen to be stored safely and densely. Also, energy savings can reduce the energy use and cost. Last but not least, we want to support the net zero, promote clean energy, and contribute to net zero carbon goals. Traditional hydrogen storage faces some challenges, like the compressed gas requires heavy, robust containers. It can result in safety issues like explosions or leaks. And the liquefied hydrogen storage requires extremely low temperature, making it complex and expensive, thus reducing the efficiency. So our solid-state hydrogen storage offers several advantages, like high volume density and safe low-pressure storage. Specifically, magnesium-based system has a storage weight density above 6 weight%. And also its operating temperature will be below 300 Celsius degree. So this approach will be utilized to utilize common and recycled magnesium alloys. This would be a large-scale process, and then make it both efficient and sustainable. Next, let's talk about our procedure. This is DK60, our magnesium alloy powder. And then we break the powder to the spherical form of the atomizer powder to always high energy ball milling to narrow scale grains. And we refine the grains to induce the defects and make the catalyst to be distribution, so we can improve the kinetics of hydrogenation. Our recent research shows that while we add 5 weight% graphene, the capability will up to 5 weight%. And if we add additional palladium as the catalyst, the capacity will reach up to 6 weight%. This show a high storage density. And then take a look at this graph. This graph shows a long-term cycling. And it is clear that the capability remains stable and the kinetic absorption haven't declined. On the other hand, we just switch the catalyst from palladium to titanium dioxide and graphene oxide. This is the narrow composite catalyst, and this change significantly lower the cost and while reaching similar performance. So we can take a look at this graph. The capacity of hydrogen also remains 5.5 weight%. So it indicates the fast hydrogenation and dehydrogenation rate. So where will our hydrogen storage alloy can be used? Our magnesium alloy could be pressed into several single slots. Each slot could be heated separately and to release the hydrogen. And then we connect to the fuel cell to provide the hydrogen energy. So for the long distance transport, it cuts down the safety concerns and the cost. So make it easier to be stored in the city. Plus, thanks to its high density and the storage properties, it could be a perfect emergency energy supplies, whether it's in rural areas or in a military basis. And this is all about our presentation. Thank you.
Thank you. Thank you, team number 6. All right. After the 16 presentation, we're going to invite our judges to move to the booth to see their demonstration. All right. So let's get ready and move on. For the teams, we're going to start from the team number 1.好，我们这边邀请评审员到我们的第1个展位。一样有6分钟时间啊。
Okay, how? Thank you. So, good morning, judges. Here we have prepared the super hydrophobic sponge, and now I will try show you the performance testing of it. Thank you. So here we can see the super hydrophobic sponge. After synthesis, the color is like a pink, and we can drop the water on top. We can see it can just stand on the sponge top. It's okay. Yeah, you can just hold the sponge top. But if we use the original sponge, after we drop the water inside, it will just disappear on the original sponge. And of course, we can test it in the water. We can see the original sponge will just fall down on the water bottom, but if we use the super hydrophobic sponge, and it will just fly on the top. Sorry, it is too big, but it will fall down, but this won't. It will just on the top, won't fall down on the water inside. So here we also have prepared the 3 different types of oil. And this is the waste oil from the mitral cycle bike. Okay. Yeah. Okay, enough. Go. Oh, we have dropped the oil in the DI water, and we can see after we put in the sponge, it can very quickly to suck the oil away. And when we squeeze it out, it will only the waste oil inside. For the simulated situation of the oil spills in the ocean, so we also have prepared the crude oil mixed with the DI water to modify the situation. Here, help me open it. 一点点，我来。So we drop the crude oil on the water top and then use the hydrophobic sponge. We can see the sponge will just absorb the oil away. And after squeeze the crude oil out, a little bit too less, yes. And this application can repeat many times until the crude oil is fully being absorbed. So, of course, in future use in the industrial application, we also have scaled up the super hydrophobic sponge. So we hope this in future will work in the industrial application. Thank you.
Yeah, I have a 3 questions for you.
Yeah.
I think you're doing such well for this oil separation.
Yes.
Do you think you can further use for other environmental pollutants, such as heavy metal and
Yeah.
VOC and some? And
Yeah.
secondly, do you think, do you have estimate your carbon footprint and the water footprint?
Oh, okay. And for the application of the adsorption, we also have tried the organic solvents. So this super hydrophobic sponge is not only for the oil, the separation, it also can use for the organic solvents. Organic solvents here we can see. Here we have tried over 10 the organic solvents, such as the dimethyl ether or the silicone oil or the methanol and the ethanol. So it actually can use in different type of the application. So not only for the oil separation, yes.
How about the carbon footprint?
Carbon footprint.
Yeah. Since you try to make the MOF, probably
Yeah.
you use other energy and some chemical in there. So in this, we are going to working on the net zero technology. So
Yeah.
you have to consider the carbon footprint as possible.
Oh, this I want to ask my professor for help.
Yes, I think the production of this material is not so costly and not so produce so many carbon calculation. And for the removal of those pollutants, I think we totally can reduce the loss of the pollutant and try to emit or remove those carbon values. Yeah, I think the result will be positive. Okay.
Have you tried different kind of MOF? Seems that the particular feature is the hydrophobic.
Yes.
Any MOF with hydrophobic will work?
Any MOF with hydrophobic is work. Actually, we have tried other different type MOF, the key point of it actually is the ligand, because the ligand is very easy for the chemical reaction. Actually, if you use like zirconium MOF or the aluminum MOF, if he have the ligand can easy with the chemical reaction with the alkyl chains, and it all can to form this hydrophobic, super hydrophobic, this type MOF. So we have tried zirconia, and it also works.
Any other questions? We have only 5 seconds left. All right, thank you very much, team number 1.
Thank you.
Okay, thank you, judges. We move to the team number 2 for their demonstration. Please hold the microphone and watch the time.
Hello. This is our novel DC-DC converter. So what we have this PV solar panel, and this is the DC-DC converter which boosts up the voltage. The problem in the conventional converters is that so they set a boost up voltage but at higher voltage cycle. So at higher voltage cycle, what will happen is like there are a lot of losses, so the efficiency is reduced. So our team, like our 2 professors from Taikada and NTNU, we have developed a new topology like this is the converter. So the good thing about the converter is that it boosts up the voltage about 10 times better than boost converter. So we also implemented a novel MPPT technique in this converter. So we tested the circuit for 2 conditions. So in first condition, our efficiency is 96%. So in second condition, when we implemented the MPPT, our efficiency is improved to 99%. So now you can see the video. Can you play the video? So this is the hardware demonstration of the proposed converter. So we have tested it for 3 conditions. So this is condition number 1. So this is DC power supply. So this is oscilloscope. And this is our proposed setup. So the condition is 1 is 35 volts. So at 35 volts and 40% of duty cycle, we get output at 381 volts. So this is the waveform of the converter. Another stage is at 45 volts and duty is 32. We reduced the duty. So this is the output of the converter, and this is the waveform at 32%. And the third condition is at 55 volts and 25% of duty, and the output is 382 volts. Okay, can you show the graph? So these are the waveforms, other waveforms of the converter. So these are other waveforms of the converter related with the other components. Like in our, the good thing about our converter is that the voltage stress across the switch is reduced to half of the voltage. Can you show the MATLAB graph? MATLAB. MATLAB. So, okay. That one. So this is the, we run a program in the MATLAB which shows what is the effect of output load on the converter. And after this, we have used the MPPT technique to coil up the gain of the converter, and it gives 99% efficiency. Okay, thank you.
Yeah, thank you for your presentation. Yeah, my question is, have you made comparison with other topology? In your topology, you require 7 diodes and I think 5 capacitors. And I don't know why is the reliability for this topology. And another one is you can see other topology. I think they can give the same booster ratio, but I don't know whether you make comparison with them. Regarding the cost and components count.
So the total cost of we use the cheaper components and they are light in weight. So the total cost of the proposed converter is 700 NTD and 23 USD. Yeah. So we have make the comparison. So on the comparison we see like other topologies, their gain is at but higher duty cycle. So at higher duty cycle there is stress across the components. So they may burn or damage, and their efficiency is reduced further because at higher duty cycle there are conduction loss, parasitic loss, and other thermal losses. So our converter, like we run our converter below 40%. So at below 40%, the converter shows us the maximum efficiency.
Okay. Yeah, quite simple question because there's a high booster ratio converter. So you got two inductors. If you have a transformer, and then you can also get a very high booster ratio. Have you made such comparison?
Yeah,
thank you.
The comparison is related with the weight because if you use the transformer, it is like I think 15 times much has much weight than our converter. So our converter is light in weight.
Yeah. Okay. Well, I don't know why you do not use a heat sink. You don't have any heat sink in your power device water.
So we use two parallel MOSFETs.
Yeah, but I cannot see any heat sink.
So we use heat sinks and fan in our lab.
No heat sink here, you see?
No, not here, but in lab we use fan.
Okay.
Yeah.
Okay, thank you.
Okay. Thank you.
Thank you, team number 2. We're going to move on to the team number 3, right over here. Okay, swear please.
喂，听得到吗 ？OK， 开始吗 ？Okay, hello everyone. We're from National Taiwan University. Hello everyone, we are from National Taiwan University. So today I want to show you our assembly technology using membrane engineering. And our core technique includes 3 parts. First, we use the highly CO2 affinity MOF. And we coated the MOF onto the hollow fibers. And also the hybrid process of membrane adsorption and membrane separation. So today I want to show you the first stage, membrane adsorption. So the as-coated hollow fiber will be sealed into the module. And when the cold fluid passes through the module, it can adsorb CO2. In the meantime, when the hot fluid passes through another module, it can dissolve CO2. So when one reaches saturation, we can change the flowing direction of the fluid so it can continuously operate it.
After the membrane adsorption, the concentrated CO2 will go through the membrane separation module. This compact module contains of hundreds of hollow fiber membranes, offers 1 square meter of membrane surface area. Just like this large surface area can be packed into this small module. And the CO2 and N2 will be get into this side. And for each hollow fiber, CO2 can pass through to the inner side of hollow fiber, but while N2 will be blocked. So we can obtain CO2 from this side, while obtain N2 from this side. After separation, we can get the CO2 with purity over 99%. In summary, AcceptMe combines 2 novel technologies, membrane adsorption and membrane separation. Due to the advantage of a hollow fiber modular design, scaling up can be straightforward and efficient. AcceptMe can save more than 40% energy consumption and reduce equipment size by 80% compared to traditional methods, making a huge contribution toward net zero emission and sustainable development. So please accept me.
Thank you. Thank you for your presentation. I just have 2 questions. Do you know there's a very famous professor, one from Ohio State University, is Winston Hall. Okay, he have some technology. The other one is from the Zhongyuan University, Professor Lai. Okay, so first question, have you tried to compare your technology with two professors? Okay. Secondly, you try using the hollow fibers module. You know we have a tubular module, spray wound module. Just my question is why you choose these hollow fibers? Okay. The third one that have to be compared with the energy consumption. Do you know the benchmark around the world? What would be the lowest energy consumption? There's 3 questions.
Okay, the first one we have compared to other work, which is Western Hall and maybe Jingyi Lai in Zhongyuan University. And we have showed a comparison performance of separation, comparison of separation performance in our PPT slide. And we have confirmed that our separation efficiency have a very high performance. Yeah. And the second one is, why we choose hollow fiber rather than spiral one is because that we have to heat and cooling down the adsorbent. But in hollow fiber, the heat transfer will be better because the adsorbent is just coating on the hollow fiber. So if we transport hot gas or hot vapor or cool water into the inner side of hollow fiber, the adsorbent will be heat rapidly, so that we can shorten the heating cycle time. So it can create it can capture lots of CO2 in a shorter time.
Yeah, probably you can produce the largest production.
Yeah, large production in the same time.
That's one. The last one is your energy consumption, the carbon footprint, as compared with others membrane technology around the world.
But we have compared we have calculated the carbon footprint in our system. We have compared that if we capture 1 kilograms of CO2, how many CO2 will generate in our capture process?
Yeah.
I have if we after the calculation, our result is that if we capture 1 kilograms of CO2, we'll generate about 0.2 kilograms of CO2. Is that actually we capture the 0.8 kilograms of CO2.
Good, thank you.
You try to get the CO2 from flue gas.
Yeah.
So how about the poison effect, such like sulfur and other things that in the...
Since our technology is focused on CO2 and N2 separation, but still we can extend our process into the SOx or DeNOx or water removal or some particle removal. Yeah, and we can, if we want to remove SOx or NOx, and we can design our membrane material to design. I want to remove SOx or NOx, so we can. If we want to remove SOx, we can design.
Quick temperature for the absorption is lower than the.
Lower than amine. Usually amine absorption is around 150 Celsius degree, but in our system we can operate just heating to around 100 or 120. So it will significantly reduce the energy.
Sometimes you have to do the treatment process
Yeah.
to protect your membrane.
Yeah, protect the membrane.
That's very important.
All right, thank you. Time's up. Thank you, team number 3. Now we're moving on to the team number 4. You ready?
Hello everyone, we are the international contest team number 4. Now I will demonstrate the practical operation of our project. This includes the preparation of the gas diffusion layer with catalyst, the APPJ post-treatment, the AEM cell, and the practical operation of hydrogen production. So nickel cobalt move on carbon paper are used as the gas diffusion layer, GDL, for oxygen evolution reaction. So first, we synthesize the nickel cobalt move on carbon paper by a simple isothermal method. The nickel nitrate, cobalt nitrate, BDC, and ethanol were used as the mixture. The mixture was then placed in an autoclave with carbon paper. The nickel cobalt move was grown in situ on carbon paper. And this is the completed nickel cobalt move on carbon paper, which will then undergo the APPJ post-treatment. The completed GDL was placed on a motion platform and scanned with the APPJ. In this step, high-energy particle and reactive species in the plasma react with the catalyst material, achieving rapid material modification. Next, I will demonstrate the AEM cell we use in this project. Below is the structure of the AEM cell we use in this project, which has a symmetric structure centered around the AEM membrane. The component of the cell includes the bipolar plate, allowing electrolyte to flow in and the gas to flow out. The heating plates on both sides of bipolar plates can control the temperature of the cell. the gaskets are used to fix the GDL. The GDL with APPJ post-treatment was placed between the bipolar plates and the AEM membrane. So next, I will demonstrate the practical operation of the AEM cell. This is the AEM cell after assembly. So using a water pump, 1N potassium hydroxide solution was delivered into the cell. Then the electrical energy supplied by a power supply starts the electrolysis reaction. And the multimeter is used to measure the voltage and the current of the cell. Then we can collect the gas produced by the AEM cell. The catalyst on the GDL can reduce the energy consumption for hydrogen production. The APPJ post-treatment can further improve listening.
I have two questions to ask. The first question, how much efficiency improve use this kind of process? This is almost the technology is not new, but you just improve some process to improve the performance. Maybe you comment a little bit about this. The second is how to you right now only a small system. How to scale up to the large system? I think this is also the major problem for this kind of technology.
Well, it's a tough question, so I have to take these questions. The first one is the improvement. We compare our system with the commercial product inhibitor system. Their energy consumption about 53 kilowatt hour per kilogram hydrogen production. And our energy consumption is around 48. So our right now the single cell is lower. And now we are trying to find funding to make stacks. And the second one is from the inhibitor is used this kind of AEMWE system. And because right now AEMWE is less mature, so they use small cell and to make a large system. It's different from AWE or PMWE. They have large electro area. So currently from the German company, the information we have is they use smaller area electrode to make a larger system. So right now, currently, ITRI has one system in Taiwan. Yeah. But so far, we don't have a chance to visit the company yet. Yes.
Okay.
Thank you.
I have a very short. When you try to compare the technology, as an environmental engineering, we have to critical access from the aspect of environmental, engineering, and economic. Okay. So my question is, for the engineering, you have to consider about your selectivity coefficient and your transport coefficient. And you do have several key performance indicators you have to be compared with the other technology.
Yeah,
have you tried to do this?
This is an excellent question and very tough question. And right now, because we don't have much green energy, renewable energy in our country, in Taiwan. So right now, a lot of arrangement they will make green hydrogen from maybe Australia or from Europe. We have so make green hydrogen and then become transportable. So far. It's a problem if we don't have much green renewable energy, if we want to produce green hydrogen. Yeah, so AEMWE is less mature, so it's still under development. But the future development is underway. A lot of people are thinking about it.
Good, thank you
very much.
Thank you very much, team number 4. Let's move on to the team number 5 for the demonstration.
Test. Okay. Hello, distinguished committee members. Please allow me to provide more information of our CWEC system. I will separate into 3 parts. CWEC experiment introduction, details for carbon footprint calculation, and environmental sustainability. First, this is our physical model. The waves are channeled through this funnel-shaped passage to concentrate them to the hydro turbine and allows the generator to produce power. And one of our CWEC application is to be artistic installations like we demonstrated here. And this is our experiment. We decided 3 channel lengths and 4 angles. It results in 12 different configurations. And we take this wave generator experiment at Taiwan Hydraulic Laboratory of National Cheng Kung University. This is the place we take experiment. And as shown in video, when the oscillatory green light is on, it means that the CWEC is successfully generated power. Please give me a second. This machine will, the green light will on when the CWEC is generating power. And this is the formula we calculate our efficiency. By calculating the power generation efficiency, we found that CWEC's efficiency can range from 75% to 85%, which is higher than traditional oscillating water column. Next is details for carbon footprint calculations. Because CWEC consists mainly of wave channels and a hydro turbine, we require 40% less cement compared to traditional OWC. And for gravel, CWEC is not need to build additional space to compress air, so we suppose we use 70% less of gravel. Additionally, we give more assumption to make our carbon footprint calculation more accurate and reflecting to real-world conditions. Finally, is our environmental sustainability. We mentioned that our CWEC could serve an artistic installation, artificial reefs, and boosting biodiversity. For artistic installation, we could provide emulation to the coastline. And our CWEC system's relationship with artificial reefs is CWEC negative carbon cement can use to artificial reefs during the disposal. And finally, the power CWEC generate could integrating a seaweed farming to enhance carbon negative benefits. And this is our presentation.
We know that wave energy tends to be low density energy. So the cost of energy production actually is important. So have you done any calculation on the cost of electricity when you generate per kilowatt hour?
We've done several experiments to calculate the cost of the energy production, but it's one of the things that we could put into further consideration into our future work. Maybe by using the AI to find out the optimization model to find like which is the best electrical cost that we could use by deploying our structure.
Yeah, I just have a very similar question. The wave energy is good. Do you know what would be the barriers you have to be overcome? This is one. And the secondly, we have to know, probably you are the civil engineering, you're much interested in the cement industry. My question is, if your technology goes successful, do you think it can be introduced into other major industry in Taiwan for the carbon reduction?
As you know that, of course, we got many barriers when we're like instructing our system and designing the stuff. But what we're trying to overcome is to use the advantage in Taiwan that we've got. Like, Taiwan is an island, and we're trying to use the advantage of the waves that are surrounding us and to deploy our system. And about the carbon negative cement, what we're trying to do is not only the water displays as the west coast of Taiwan, we could also use it in the the net zero, the other construction to build some stuff by using not the normal cement, but the carbon negative cement to absorb more CO2 in the future by using this to build like different buildings. Yeah.
Yeah, thank you. My question is, you have a freewheeling energy storage system. What is the efficiency of the whole system? Okay. Because that's 9.7, right? Yeah, I don't know what is the efficiency here. And you multiply together, yeah, what is the result? Thank you.
The actual thing that why we're employing this one is because the wave energy is intermittent. So like the waves don't go like sometimes like in a reasonable way. So when this doesn't work or it's operating with low energy, the flywheel's energy storage system could provide extra energy when this isn't going well. Yeah.
Efficiency for this stage, for this FESS.
The efficiency of this is what we're trying to do is if the electricity that it's produced doesn't meet the grid code, and this is efficiency we're trying to improve by deploying the flywheel energy storage system. Yeah.
We know more stage, less efficiency. Yeah.
Thank you. The last one and finished. All right, the time's up. All right, thank you. Thank you, team number 5. Let's move on right over this way to team number 6. It was the final at this period of time. After this, we're gonna have a short break. All right, team number 6, your time.
Okay, hello, Georges. Hello and welcome. We're team number 6 from National Taiwan University. Today, I'll be presenting you the latest technology of magnesium-based hydrogen storage alloy. I'm starting from the base material over here. It's a material called ZK60, which is a magnesium-based alloy consists of multiple elements, including zinc or zirconium. Now, traditionally, the processing of ZK60 from raw material all the way to powder is by trimming, chipping, and finally ball milling, which is very time-consuming, expecting time around 60 hours or even longer. Whereas the processing process that we're currently using called optimization powder process, as you can see on the poster over here, cut down the time significantly all the way down to around 5 hours, which I think is very impressive. And not only just it's very time efficient, also our ZK60 is produced mainly by recycled materials from industrial waste or civilian use. Now, a little bad news of this ZK60 powder is that it cannot perform that well at ambient temperature and the raw material itself. So we have to add in hydrogen storage catalyst materials, which is this over here, these 6 material list over here, which is tested multiple times by our laboratory of the research over this past years. Now, adding catalysts into hydrogen storage alloys is not something new in this territory. However, I think we managed to use materials that with relatively low cost, like graphene oxide. The reason why you see a lot of graphene oxide is because it serves as a 2-dimensional materials that creates a great coverage over the ZK60 optimization powder. And not only the coverage, also it creates a sitting point of additional material like transition metal oxide or boron nitride oxide or so on, which serve as a little particle that can decompose the hydrogen gas among attachment. And after that, the 2-dimensional graphene oxide serve as a tunnel and navigates all the hydrogen atom into the interior part of our powder. Okay, so to make all these laboratory big head to put into practice, we even design the complementary reservoir on ourselves. So this hydrogen storage reservoir right here is also exclusively designed by our laboratory, like 2 years ago, I believe. And it contains of 2 major parts, the interior part, the interior cylinder, and the exterior one, like this. So as you can see, it is a very porous design, and that allows power to sit inside and also allow hydrogen to flow smoothly and penetrate through all the sections. And followed by that, the outer part of this cylinder is a heating device. Just like I've mentioned, this material cannot work very well at ambient temperature, so we have to heat it up to like around 300 degrees Celsius. By plugging this socket from the power supply, we can have this cylinder automatically work at a design temperature that we're looking for. Now, up from here is our direct competitor, which is conventional, like ambient temperature condition hydrogen storage alloy. And it is lithium-based material, which is very expensive, as all judges you can expect. And also, the performance is not so well compared to our research. Only looking around 1.28%, whereas you can see on the poster right here, we can boost up our storage capacity all the way up to 5.5 to 6.58%. So to wrap up this presentation today, I think the technology that we're currently touching on has multiple advantages over conventional hydrogen storage technology in terms of time consuming and cost, safety, storage capacity, and also I think to stick around the title we're looking for today, net zero technology, we're using like nearly 100% of recycled materials. So I think the future of this technology is very bright, and right now I'm going to evacuate this place for all of you, and you are very welcome for some opening question. Thank you.
It's just a very short question. I think you're doing quite successful. Have you tried to using the life cycle assessment to do the further life cycle assessment from the entire? Okay, yeah, that's the thing. Yeah, 生命周期 ，OK。
我不知道哎。
Have you done any research on the lower the desorption temperature?
Oh, yes. So the cycling process has been tested multiple times by 300 Celsius degree, 300, all the way from 300 to 280 and to 260 all the way down. We've even once tried to lower it all the way down to 200, but it needs more like advanced technology in catalyst, because like catalyst is the one that changes the absorption and dissorption kinetics of our material. So we're still looking for like newer technology in catalyst, but I think that can be well expected, because the one performed with like 240 is around 4% I remember it. So I think we're very near of using a relatively lower temperature close to ambient temperature.
I think this kind of material belong to the metal hydride. In the past, many people study the metal hydride material or hydrogen storage, but they had a couple problems. One is the weight problem. The other is the volume problem.
Yep.
And another is already mentioned is you want to release hydrogen. You will need a high temperature.
Yep.
You need high energy input. Can you answer this?
Okay, so I think that's something like complementary to our research. It's because since we have a higher storage capacity, right? So we can like grab a little portion of the hydrogen storage inside, let's say like 0.5% to produce heat for itself, for a desorption itself, understand? Because since we have like a great margin of a greater performance compared to conventional storage process, yeah, so we can have like some extra power storage inside. Yes, we have to.
Okay. All right. Thank you, judges, and thank you for response from the team. Thank you. All right. It will be end of this section. All right. Dear judges, now currently we have the 15 minutes to take a short break. So the next session will start from 10:40. It's about 15 minutes away. So now it's time for take a rest. All right, judges, Ladies and gentlemen, now we're going to start our second section. There will be another 6 teams on the stage to do the presentation. Now we're going to the team number 7. Now is your time, please. 好，第7组请上台准备。
Hello, Taiwan. So today we'll introduce Ecosphere, our innovative project that is designed to achieve net zero emissions by 2050, a new model for sustainable and effective learning environment. We are from Sunway University School of Engineering and Technology and School of Arts, and we traveled all the way from Malaysia to present our work. So this is our Ecosphere building project that is designed to a 7-story building for 1,200 students. It is designed to, it features classrooms, laboratories, and also some studios. So it focuses on demonstrating net zero emissions by improving the embodied carbon emissions from the construction and the operational carbon from the daily energy use, focusing on Scope 1 and Scope 2 emissions. So to achieve net zero emissions by 2050, Ecosphere employs 3 key strategies: TerraGuard for eco-friendly materials, Aquazen for passive cooling to save energy, and then Airscape for smart energy management with AI and solar panels. So these key strategies can reduce CO2 emissions from solid, liquid, and gas. So let's start with discussing the first component of the project, which is TerraGuard. So TerraGuard reduces the embodied carbon using low carbon materials and carbon negative materials. So cement and steel are the top contributors of CO2 in the construction industry. So, but what can we do about them? So by using 50% or replacing 50% of the cement from the, with our GGBS, into the precast concrete construction, we can reduce CO2 significantly. Although the carbon uptake coefficient is significantly lower, we can still reduce the embodied carbon by 468.7 tons of CO2. So in our project, we use waste materials. We convert waste materials into a valuable material. So how does this work? So by recycling, by incorporating recycling methods, we can reduce the carbon emission by 4.5 tons of CO2. So next is the sustainable materials for furnitures. So for the furnitures, we can actually we convert the traditional materials with low carbon materials and also wood that are sustainably sourced and that can absorb CO2. So by doing so, we can reduce the embodied carbon by 76.3 tons of CO2. And lastly, we need to furnish our building with paint. So we use carbon capture paint. So how does this work? So we use low VOC materials, and we apply our nanotechnology with graphene and also lime that can absorb CO2 from the air, thereby reducing embodied carbon by 5.5 tons of CO2 from this particular part of the construction. So in summary, we can reduce the embodied carbon of the construction by applying greener alternative materials, adopting precast construction materials, and also by also recycling. We can thereby have a net carbon emission of 429.6 tons of CO2. And Andrea, the floor is yours.
Okay. All right, thank you so much, Jared. So I'll take over from Jared from now on. Okay, so as we move on from TerraGuard, we dive into Aquazen, where we see water and innovation flow in sustainable space. So first of all, we have our heat insulating fin. The east side of the Ecosphere building is actually painted with nanocomposite barium sulfate paint that efficiently absorbs solar radiation from the sun, cooling our building from 31 degrees Celsius to 28 degrees Celsius, thereby reducing our carbon by 11.6 tons of carbon dioxide. Now, moving on, we outsource our cooling to a central chiller plant which uses high-efficiency chiller systems as well as advanced renewable technologies, reducing our carbon dioxide emissions by 37 tons of carbon. Now, we also have rainwater harvesting. So when it rains, none of that precious rainwater goes to waste. So we use it to actually use for restrooms as well as irrigation, reducing carbon emissions by 1.4 tons of carbon dioxide. Okay, now we have Escape, where we optimize energy consumption and provide clean energy for our occupants. Okay, so first, how do we use our energy? We have the ACMV energy recovery system. So we reduce carbon emissions by 41.3 tons of carbon dioxide with an efficient heat exchanger. Then we have the BEMS system that optimizes energy consumption to reduce another 23.7 tons of carbon dioxide. And finally, N-type PV panels and an AI microgrid to provide clean energy for our occupants to reduce another 299.1 tons of carbon dioxide. All right. Tying it all together is our digital dashboard, which optimizes energy consumption while providing real-time data trends. Okay, combining it all together, we have 414 tons of carbon reduction and also a negative offset of 30 tons. Repeating this year on year, we're able to achieve net zero in just 19 years. And so, join Sunway University as we revolutionize the construction industry to create a cleaner, more sustainable net zero planet. Thank you.
Thank you. Team number 7, thank you very much. Now we are moving on to team number 8.
Good morning, judges. I'm Deb, and today I'm going to present our research topic, which is novel process design and validation for decreasing carbon dioxide emission from cement production decarbonization. Our team, Our team is headed by Professor Wu from the Department of Chemical Engineering and Professor Lai from the Department of Civil Engineering. It comprises of 4 master students, including me. We know that climate change is a major concern for everyone. Whether you be coming from any part of the world, we are all facing its challenges. Researchers also say that it's going to be severe in the coming year. One of the major reasons for climate change are the industrial effluents. Cement industries alone contribute to 7% of the global carbon emissions. Not only that, they also generate solid toxic residues, which the industries find difficult to deal with. Hence, if we are able to provide a solution to deal with such wastes in an eco-friendly manner, they might have huge economic potential. We know that cement is a major ingredient in the concrete mixture. The quality of the cement determines the strength of the concrete. So, to study industrial processes, we need something which can mimic the industrial process accurately, and hence, our team has used Aspen Plus simulation software to modify the process. First, we design the model with reference data. Second, we feed in the chemical and material properties. Thirdly, we validate the simulation results with real-time data. And finally, we optimize the entire process to make it economic and eco-friendly. So this is how a conventional cement plant looks like. It has different zones, but our major concerns are Zone 5 and Zone 6, which is responsible for majority of the carbon dioxide production. So we propose to solve this solution using 3 novel processes. First is the CLP, or calcium looping process. The second one is the TEG, or triethylene glycol physical absorption process. And third and most important one is MCCKD, which stands for mineral carbonization of cement clean dust. Before we talk about these in detail, let me just briefly introduce the process. So this is the preheating process where it prepares the raw material using hot air for the clean process. And second, in the clean process, the clinker formation takes place. The temperatures are above 1000 degrees centigrade. So this is, as I said before, we have used Aspen Plus simulation software for our study. And this is how the cement plant looks like. The point to note here is the conventional cement plant releases to around 266 tons of CO2 per year. So we have added our novel processes in the sidelines without changing the existing systems. And hence, it's exactly feasible and compatible with the existing cement plants already there. So let's talk about these processes in detail. The first one is the calcium looping process, where it captures the carbon dioxide coming from the preheating cyclones and converts it into carbonates. These carbonates are later moved on to a second reactor, which is the calciner, where it decomposes to form the carbon dioxide having a purity of 96%. What if I tell you we can sell this carbon dioxide? So we add a second process to increase the purity of the carbon dioxide and make it till 4N grade. The 4N stands for 99.99% purity, which is a commercial grade for carbon dioxide to be sold in the market. So this uses the TEG process. And finally, coming to the most important part is the MCCKD process. This is where we store the carbon dioxide in solid residue. In this process, first we remove the solid residue using the ESP, and later send it to a two-stage reactors. The first one is the extraction process, where we use solvents to extract important ions from the solid waste and convert it into carbonates, and convert it into an ionic liquid. This ionic liquid is later sent to a second reactor, where using high pressure, we react the CO2 with the ionic liquid. So, or rather, we call it store. So these form the cement additive. So overall, we can see that the MCCKD process not only uses the CO2 as a gaseous waste, but also the solid waste to form cement additive. In the brief interest of time, let me discuss the most important results. The conventional cement plant releases around 266 tons of CO2 per hour. And our novel process has managed to decrease that to 2.11% of its original value. Not only that, we are able to store around 12.33% as in the storage, and most of the carbon dioxide, which was previously being released as the gaseous waste, is being sold to the market to make money for the industry. So overall, we can say that the novel process is a better choice compared to the conventional cement plant, where the waste is just let out in the environment. So the CO2 has varied range of applications, starting from soft drinks, welding machines, etc. And it has a market value of 1.29 USD. So money, right? And when we see our cement, the strength of the cement is the major concern for every industry. Our novel cement claims to have better strength when compared to the ordinary Portland cement. In conclusion, we can say that we are not only achieving net zero emissions from the from the cement plant, but using the concept of CCUS to make money, to recycle waste, and provide a greener and sustainable environment. Thank you so much.
Thank you. Thank you, team number 8. Now we're moving on to the team number 9 for their presentation. Please be ready.
Hello everyone, we are team number 9. Today we are honored to present our innovative desalination technology, redox-mediated bipolar membrane electrodialysis. This next generation desalination technology is designed for the dual purpose of seawater desalination and carbon capture. The rapid industrialization driven by human activity has caused climate change. The accumulation of CO2 in the atmosphere has led to global warming. In response, Taiwan's government has officially announced the net zero transition milestone for 2030, aiming to reducing carbon emissions. Moreover, the issue of water scarcity is becoming increasingly severe. The seawater desalination is a promising way to remove a mineral component from the seawater. However, the seawater desalination treatment plant in Taiwan often require high energy consumption, consuming around 2.4 to 5 kilowatt hour per cubic meter. One of the most commonly used desalination technology, electrodialysis, often require high energy consumption. The high energy demand results in high carbon emissions. To address this issue, it is critical to develop energy-efficient desalination technology that can achieve net zero carbon emissions. While energy efficiency is a key concern, Addressing water scarcity and carbon emission is equally important. So, develop a novel water technology that can recover water and mineral resources is critical for sustainable future. Nowadays, bipolar membrane electrodialysis has gained lots of attention due to its ability to induce pH swing on both sides of the membrane, converting salts into acid and bases. However, conventional BMED system require high driving voltage. Our team has addressed this limitation by developing redox-mediated BMED system. This innovative system integrates redox-mediated electrolyte with BMED system, significantly reduce the energy consumption required for operation. Moreover, the system can be powered by the solar-generated electricity. Our system replaced conventional 4-channel design. The innovative 5-channel system design enables simultaneous seawater desalination and carbon capture. The experimental setup includes a solar panel for power supply and a redox-mediated BMED cell with alternately arranged bipolar cation and an ion exchange membrane. After 60 minutes of operation, the conductivity of the synthetic seawater in the dilution chamber decreased from 49 to 46 millisiemens per centimeter, demonstrating its ability to achieve efficient desalination over a wide salinity working range. Moreover, the pH in the alkaline chamber significantly increased from 7.9 to 10.2, creating optimal conditions for calcium carbonate and magnesium carbonate precipitation to achieve carbon capture. The redox BMED system can achieve low molar energy consumption of 3.6 kilojoule per mole. Considering a daily water treatment volume of 100,000 tons, the CO2 capture capacity of the redox BMED system is nearly equal to that of 3 Da'an forest parks. The technical value of the redox BMED system lies in its energy efficiency, operates at low energy consumption with solar power. And it can produce 2.6 metric tons of calcium carbonate while removing ions from the high saline water. By using this innovative technology, we can achieve the Sustainable Development Goals of 6, 11, and 13. Thank you.
Thank you very much, team number 9. It's time we are moving on to the team number 10 to come onto stage. Have your presentation, please.
Testing. Good morning, ladies and gentlemen. I'm Justin from team number 10 of the international contest. We are researchers coming from the Hong Kong University of Science and Technology, led by Professor Irene Lo and Dr. Zhe Xiaozheng. We are here today to present our innovative research on a multifunctional photoelectrochemical system for sewage treatment, which can meet the discharge standards, lower the carbon emission, and generate green hydrogen. There are 3 limitations in conventional wastewater treatment. The first limitation is the intensive carbon emission, mainly comes from the nitrous oxide and methane generation, contributing to 5% of the global non-carbon dioxide emission. Second, the high energy consumption, primarily coming from the activated sludge process and contributing to 3% of global energy consumption. And third, using chlorination for disinfection will incur high chemical costs and generate carcinogenic disinfection byproducts. We find that there's an opportunity for us to overcome these three limitations in Hong Kong. It's because in Hong Kong, we use seawater for toilet flushing that generates sewage with a high chloride content, favoring us to promote a chloride activating PEC system for sewage treatment. Therefore, we are inspired to design a novel PEC system to simultaneously degrade multiple pollutants, minimizing the carbon emission and DPP's formation, as well as generating hydrogen gas as green energy source. In order to prove whether our ideas works or not, we divided our research into two main stages. We first conducted a laboratory study by the batch reactor in order to investigate the performance and the mechanisms of the PEC sewage treatment. And following that, we upscaled the large-size PEC reactor according to the results from the batch study. And with that in hand, we developed a large-size PEC reactor for the continuous flow sewage treatment in order to assess the practicality and the feasibility of our system reaching net zero wastewater treatment. The key innovation of our research are the creative use of the PEC technology itself multifunctionally and the innovative designs in the photoanode material. Therefore, we have started with our batch study, which demonstrates that within only 2 hours of PEC treatment, it can degrade 100% of ammonia nitrogen, 78% of COD, and reaching full inactivation of E. coli, along with the significant generation of hydrogen gas. With the outstanding performance of our PEC system, we further found out that the reactive chlorine species contributes mainly for the degradation of COD and ammonia, as well as the E. coli inactivation, while the electrons is responsible for the hydrogen generation. It is easy for us to imagine that if we simply upscale our PEC system without any design considerations, it won't work due to reasons like dead zones or insufficient photoanode area. Therefore, our designed PEC system features 5 breakthroughs. We first increase the area and the number of the photoanodes inside the system in order to ensure the contact with the sewage and also to maximize the sunlight absorption. The third breakthrough is that the top fixed design of the photoanodes can prevent the impurities from blocking the sunlight. And fourth, the bottom-up flow design can prevent the formation of dead zones and promote well mixing. And finally, using graphite as the electrode holders can minimize the cost and prevent corrosion. Through operating our large-size PEC reactor for real sewage treatment, we found out that the treated sewage can fully meet the discharge standards of wastewater treatment plants in Hong Kong. And also, the quality of the effluent samples from the large-size reactor is even better than that from the batch reactor, showing the technical value of our reactor design. Further focusing on the carbon emission, we found out that our system can reduce the generation of methane and also nitrous oxide, along with the 95% reduction in total carbon emission, demonstrating its possibility to reach net zero wastewater treatment. So in order to show the socio-economic benefits of our system, we would like to give you an example over here. Imagine that we are applying our system to a real wastewater treatment plant in Hong Kong. We found that it can reduce over 300,000 tons of annual carbon reduction, giving around $50 million of economic benefits from the carbon offsetting, and generating around 470 million kilowatt-hour of green energy, equivalent to the demand of around 100,000 households in Hong Kong. To summarize, apart from meeting the discharge standards, our PEC sewage treatment system can also reach 3 beauties: the ability to reach net zero wastewater treatment, the generation of green hydrogen, and also the reduction and disinfection byproducts. Thank you very much.
Thank you very much. Now, dear judges, the next team will be 11. They will be online. Okay, so we're going to put their video on the screen, and they are going to do their presentation. So please, eyes on the screen. And we welcome the team from Denmark. Hello, Denmark. We cannot hear your voice. Can you try to enlarge or
okay.
unmute? Thank you. Yes, good. We hear you clearly.
Yeah. Okay. Thank you so much. And so you can hear me right now? Okay. Good morning, respected judges and experts and friends. My name is Xin Wei, and the leader of the 11th international team is Power. And first of all, it's a great honor to participate in the contest. And I apologize that due to some issues, our team was not able to attend on site. It's a pity we could not meet, but anyway, thank you so much for your support and the professional review. And our team is from Aalborg University, Denmark, and supervised by Professor Huai Wang, who is a member of the Danish Academy of Technical Sciences. And also our team has 5 PhD students, and over the past years, we are dedicated to the reliability analysis and the design of net zero energy systems. And before introducing our products, I would like to first clarify our creative motivations. And as we all know, with the rapid development of power electronics, renewable energy now dominates the global electricity market. However, subjected to the operational and environmental stresses, unscheduled failures of power electronics always occur. This reduces the sustainability and the efficiency of renewable energy systems, and also increases their maintenance cost and environmental pollution. So an innovative condition monitoring solution is urgently needed to improve their reliability and sustainability. And Essence Power, developed by our team, is the world's first non-invasive condition and health monitoring solution for renewable energy systems, which can effectively address their critical reliability and sustainability challenges. It acts like a dedicated doctor with the diagnostic and prognostic capabilities, promoting the more reliable, sustainable, economical, and environmental friendly renewable energy systems, so facilitating the achievement of net zero emissions. And Essence Power is mainly composed of 3 parts: an Essence Power sensor, an Internet of Things platform, and an intelligent brain. Essence Power sensor is a hardware-based device for collecting the operational and health information of renewable energy systems. And it offers non-invasive interfacing and multiple versions, and can be designed in a system for in-suit operation and or designed with hand carry requirement for service. And the IoT platform in the Essence Power is responsible for the data transmission between the Essence Power sensors and the intelligent brain, as well as a robust data storage. Also, it provides user-friendly interfaces, allowing the user to monitor the renewable energy systems by their PCs or the mobile phones. And the intelligent brain is the core engine of the Essence Power. It's equipped with advanced AI algorithms for data processing. It supports the operational and healthy status assessment for the renewable energy systems, and also the prediction of their potential failures and the remaining useful lifetime. So, based on this, we can achieve informed decision making, including the operational optimization and the proactive maintenance. And from the technical point of view, Essence Power features non-invasive and high safety. It supports self-powering and plug and play, and it's scalable for various types of renewable energy systems. A simple installation enables comprehensive monitoring, and Essence Power can help you to achieve greater cost effectiveness and size reduction. And in terms of technical value, I think Essence Power enables a renewable energy system with diagnostic and prognostic capabilities for the operational optimization and predictive maintenance. And this can greatly enhance their availability and efficiency. And also with the zero failure period, the system downtime losses, maintenance costs, and pollution can be minimized, improving their economic and ecological benefits. Overall, Essence Power will set the new reliability and sustainability standards for the renewable energy and contribute to the global environmental protection and the net zero emission targets. And the rapid expansion of renewable energy has provided greater promise for the Essence Power, and its expected market include the high-speed train, wind power, e-mobility, and industrial drivers. And to achieve the commercialization, our team has set up a company called Langhai and support multiple sales models. And here is our fourth generation product, and it has been granted as a US patent. And if you are interested in testing our prototypes, please contact us, and they are offering right now. And I believe together we will contribute to a better world, and thank you so much for your attention.
Okay, thank you. This is 6 minutes main presentation by the team from Denmark. But currently, hello, presenter, we are going to give you extra 6 minutes because you cannot demo on site. So the following 6 minutes are going on, and this question from our judges. Give them. All right， 好 ，OK， 那他们有摊位，所以我们还是按照原来的进行方式。好，谢谢各位评审啊。OK， now we're moving on to the next team to do the presentation, please.
Good morning, dear committees. We are a team from National Yangming Jiaodong University. We built up a rechargeable zinc-air battery enabled by a solid hydrogel electrolyte, which can be used in both atmospheric and low-temperature environments. We believe this is a key for the next generation energy storage system. Huge emissions of greenhouse gases have caused global warming and climate change. The world is committed to getting rid of fossil fuels and developing renewable energy. Because of the volatility of renewable energy, there is an urgent need to develop a high energy efficiency energy storage system. This table shows that the current prevailing energy storage system is dominated by lithium-ion batteries. This table shows that the practical energy density of the cutting-edge lithium-ion battery is close to its theoretical value, so the development speed is expected to slow. The next generation energy storage is the metal air battery. Due to the use of endless air and its ultra-high theoretical energy density, it is full of imagination. The practical energy density of the state-of-the-art zinc-air battery is close to lithium-ion batteries, and its theoretical energy density is as high as around 1,000 watt-hour per kilogram, which shows high potential. In addition, the Earth's zinc content is much richer than lithium's, and the cost is also much cheaper. The biggest challenge with the state-of-the-art zinc-air battery is reversibility. Compared to conventional alkaline liquid electrolyte system, our zinc-air battery that can charge and discharge for more than 1,200 hours. Under the same charge-discharge conditions, our zinc-air battery displays a gravimetric energy density of 590 milliamp per hour per gram, a value greater than 160 of lithium iron phosphate batteries. a unique solid electrolyte and a unique peroxidized zinc-based nanocatalyst realized this breakthrough charge-discharge reversibility. Under the control of interfacial reactions, air can enable reversible redox reactions with nanocatalysts. For electric vehicles, they are a disaster at high latitudes. This is because the electrolyte solidifies and crystallizes easily at low temperature, causing ion transport to fail. But our solid electrolytes are incredibly resistant to solidification at low temperature. At minus 40 degrees Celsius, our zinc air battery still works perfectly. We compare the cost of our zinc air battery with the LFP coin cell with the same power generation capacity of 1 kilowatt hour. The price is based on raw materials, including cathode, anode, electrolyte, separator, and current collectors. Our zinc air battery costs only 21.6 US dollars, while the LFP coin cell costs up to 174.6 US dollars. Now, we further compare the carbon emissions of our zinc air battery with the LFP coin cell. The carbon emissions is based on raw materials usage. The carbon emissions of our zinc air battery is only 5.1 kilograms carbon dioxide equivalent, but the LFP coin cell is up to 16.2. The zinc air battery can be integrated with renewable energy and industrial electrolytic hydrogen production. The zinc air battery can be charged by blowing air through the hydrogen evolution outlet, combined with the input electricity from renewable energy, enabling reversible charge-discharge. This not only reduces the purification cost of electrolytic hydrogen production, but also maximizes the use of energy, the energy from air. Yeah, from air. And the fully charged zinc air battery can be used independently in electric vehicles, achieved through air blowing of pumping compressor system, or integrated with hydrogen for hybrid vehicles. Finally, we demonstrate the integration of laboratory-scale electrolytic hydrogen production with our zinc air battery. The zinc air battery we developed is expected to replace the lithium-ion batteries with lower cost and higher energy efficiency, although we still require more improved supporting sectors. This is our team. Under the guidance of Professor Ta-Chong Liu, our team is committed to developing new strategies to answer major social problems through the knowledge and technology of material science and electrochemistry. Thanks for listening.
Thank you. Thank you, Team 12. Now, at this time, we're going to move our judges to their booth to see their demo. Please, this way.
Test.
Hello, good morning everyone. We are Ecosphere team from Sunway University, Malaysia. You can see from our previous slide, this is our Ecosphere building, and this is our 3D model with 1 to 200 scaling. This is our interior views for Escape, TerraGuards, and Aquazen. This is the labs, studios, and classroom. You can have a look. Following on, this is our material boards for TerraGuards. This is for ceiling and wood panels that is used bio-treated and fabric back vinyl to be the materials is eco-friendly and sustainable. Going on, this is our terrazzo tiles for tabletops, and the color swatches, we want to match it with our TerraGuard concept that is earth tone. And this is our carpets that is 100% PP Twistex, that is non-toxic materials and eco-friendly. And last, the two tiles we have for walls and floors, that is structure finishes, is tough and safer for wet and durability. That's all for me. I will pass to my team member.
Thank you, May. Very good morning. I'm Louis. I'm the team leader for this team. And over here, I'd like to introduce, this is a net zero building that we are building. We incorporate over 10 work packages in it. And then what's so special is that we actually do not use any architectural net zero design. So there's nothing complicated about it, and there's not a costly design to it. What we do is we put in 10 net zero technologies to achieve net zero. So from the slides that you have seen, first, the building is built by green concrete. We also have a rain harvesting system, and it is cooled by a very efficient district cooling system. To manage all of that, we have a BEMS system, a building energy management system that manages all of it. Now, I'd like to bring your attention to the east wall, where we put in heat reflective paint. So you can see over here that the Ecosphere building is actually cooler than a building painted by normal exterior paint. So that saves passively, without doing anything, you save cooling energy. And then the other part is the air conditioning energy recovery system. So this is a counterflow indirect heat exchanger. It preheats or pre-cool your fresh air. So fresh air in Malaysia is warm. Instead of 40 degrees, cooling it to 23 degrees, after the heat exchanger, you use exhaust air to cool it. Then you're only cooling it from 28 degrees to 23 degrees, saving about 66% of your cooling energy. And this is also applicable in four seasons country like Taiwan, where you can preheat during winter. Lastly, I'd like to show this microgrid. When we talk about microgrid has a power source. We use solar panel, a load, a battery system, and it's controlled by an energy manager. And our energy manager is AI-enabled and also programmable. That allows us to optimize our energy flow. Therefore, we can have a negative operational energy, allowing us to offset our embodied carbon.
Thank you. Thank you, Louis. So according to our presentation, we can see that TerraGuard is a feature where it reduces embodied carbon during the building construction phase. On our dashboard, using predictive analytics, we can forecast how much of carbon dioxide is being reabsorbed into the green concrete over the upcoming years. We can also track the waste management, and also, thank you, Louis, we can also measure the air purifying paint's performance. As you can see, for an example, the paint performance may reduce over time, maybe due to its capacity, maybe due to its reaching its capacity. It will notify the users for a change or a repaint. Moving on to Aquazen's dashboard. Is the same as Escape as well. So it measures the cooling efficiency and also the temperature regulation. Through our data-driven models, we can anticipate how much of a cooling demand required, and we can adjust the system load accordingly. Remotely monitoring the rainwater harvesting system also allows us to contribute to the sustainable efforts. And
so I would say in conclusion, this allows management and the user to be able to make informed decisions on how your building is performing and how you want to move forward with it. Thank you very much. Is there any questions?
Special question. Do you receive a Green Building Award for any recognition certificate, based on your Ecosphere technology?
Yes. Okay, I would like to emphasize that this is a real building. The construction of the building has already started, and then it will be completed in year 2026. We will be GBI Gold Standard. And then with that, we also cover Scope 1 and Scope 2 emission. The life cycle analysis is being taken care of. We talk to our vendors. We make sure we know where our materials is coming from. So every carbon is recorded and calculated.
I think you mentioned about a green building, also zero energy house. In general, we have to follow three very fundamental important theory. One is called a passive house from the German practice. Yeah. Secondly, I believe you're using the green construction materials. That's the second one. The third one is a so-called system energy optimization. Okay, so my question is, how did you get the general principle from the German practice by using the passive house? And then secondly, the question is, do you using the ISO 14000 and the ISO 5001 is a kind of energy management systems?
Yes.
Okay, that's two questions.
Okay, I would say
All
that I tried my best to explain that. So I hear the question about embodied carbon construction, and then about passive, and then also the energy management. So how we manage it is, at first it was actually a little bit intimidating. What we decided is that we actually manage it through three scopes. TerraGuard will look at embodied carbon, and then AquaZen is all about the passive cooling, and then AirScape is where we look at active energy generation and energy management. And we do look at the ISO documents. In fact, some of our data is actually based on there's a Europe standard on how BEMS system work. We do refer to all the standards in our calculations.
Thank you very much. Yeah, our time is up. Okay, we're moving on to the team number 8.
Thank you very much.
跟各位提醒一下啊，6分钟包括实作跟 Q&A， 请各位注意一下时间啊。
So, okay, can I start? Okay, good morning, judges. Our team proposes a practical model to reduce carbon emission from cement industry. Right now, let me show you how we reduce carbon emission. The first part over here is called a handling part. We use this part to handle our raw material first, and then we send this raw material to zone 5 and 6, which consists of plating system, precalciner process, and the clean process. There will be a significant amount of carbon emission from precalciner process. Besides that, the clean process can produce a clinker and some solid waste at the same time. This solid waste is called cement clean dust, or CKD. I'll talk about how we treat this CKD later. But right now, let me focus on our carbon emission problem. In order to deal with such significant amount of carbon emission, we add 3 novel technologies to capture, purify, and store CO2. The first one is over here, which is called calcium looping process, or CLP. We want to use CLP to capture CO2 from this flue gas. So first, we inject flue gas inside the carbonator. In carbonator, CO can combine with CO2 to form CaCO3. After that, the CaCO3 will be sent to another tube, which is called calciner. In calciner, CaCO3 will be decomposed to Cl and CO2 again. So during this process, we can get a mixed gas over here, and the purity of CO2 is approximately 96%. However, this purity is not enough for industrial product, so we need to use another technology to purify it. The technology we choose is called TG process. And the reason we choose this process is because the main component of this mixed gas are water and CO2. If we use TG process, it can remove the moisture of this mixed gas very easily. That is why we choose TG process. So after that, we get a CO2 gas product over here, and the purity is around 4 level. 4 level means the purity is 99.99% and can be the commercial product already. Coming to the final part, but also the most important part in our study, MCCKD technology. We want to use this technology to store CO2 in CKD. However, before the storage process, we need to extract our CKD first, then produce some ionic liquid over here. And then we send the ionic liquid to next reactor, which is called perivessel. In perivessel, we inject CO2 inside. That CO2 can mix with ionic liquid to form some solid residue over here. This solid residue is called cement additive. And right now, how this additive can be used in our study? We can use this additive to enhance the performance of our cement. Please look at our poster right now. We make a table to describe the comparison between the ordinary cement and our new cement. As you can see, our new cement is better than the ordinary one. Additionally, we also make a chart to show the carbon emission of conventional cement plant and our novel cement plant. As you can see, our novel cement plant is very close to net zero emission. So it's proof that our technologies are very useful to decrease carbon emission. So in conclusion, our process not only produces a cement additive, but also reduce carbon emission. And so I can say we achieve the goal of CCUS. And our process is an attractive idea for Taiwan's cement industry in the future. Thanks for listening.
Thank you.
Thank you very much for your presentation. I know you are going to demonstrate your technology, okay? So I just questions, have you tried to compare your technology with others' technology, especially for the Taiwan cement, Taiwan 水利公司, they have some technology. Have you compared with them? And secondly, I believe your product should be compared with traditional Portland cement. Okay, the Portland cement do have some criteria and standards in terms of for STM or the CNS. Okay, the last one, I believe you have to do the life cycle analysis for the total quality management. Okay, yeah.
Thank you, Professor. Thank you for your question. I have the mic. So as for your first question, if we have compared our cement plant with an existing technology. So as we said in our presentation, we built the cement plant using reference data. Those reference data are already existing. So we have this, the white area is already existing, and the colored ones are the new process, which has been added to the existing process. So this is our build-up on the reference cement plant, which is already existing. As per your second question, when comparing our cement to the ordinary Portland cement, we can see that our cement is better. And these are the quality as per the standards for the comparison for ordinary Portland cement and our CaCO3 cement, which is obviously a better choice in compared to strength. As to answer your third question, which is the life cycle analysis, when it comes to the process, this is, we have used Aspen Plus simulation software, which is, and for life cycle analysis, we use a different software called a SEMA Pro. So we are still working on that one, but definitely that will be a next stage for this. Thank you, Professor.
Cost-wise, you have to spend like how much in US to reduce the CO2 by 1 ton? Based on the number there.
So as you can see,
that's 1 bag,
yes,
not 1 ton.
That's 1 bag USD. Yeah. So the conventional cement plant is, cement is available for a cheaper price. But when you are building a home, you want it to long last, right? So in terms of strength, you are about to spend a bit more, but it will be a long-lasting solution for your problems.
All right.
Yes, Professor. So as I said before, we have an existing cement plant. Whatever energy is being used, it also utilizes the same energy to capture the carbon dioxide and convert it into residues. So basically, our carbon footprint is negligible. So the main energy is through the burning of the fuels. So hence, that is compared, like reduced. Thank you, Professor.
Good. Thank you very much. Now we'll move on to the next team, number 9. Presenter, please.
Hello everyone, we are the group 9 and this is our experiment, and let me introduce. This is the 5 chambers redox mediated bipolar membrane and electrodialysis system for the carbon capture and the seawater dissociation. And we can see the seawater introduced into the system, and the bipolar membrane will recruit a lower voltage to create the basic and the AC environment according to the membrane and without the chemical addition. Okay, so we can see the back chambers, the carbon dioxide will become the carbonate, and the carbonate will revise the carbonate and negative ions to become the carbonate crucible, okay? And a treatment, the carbon capture. And the desalination chambers, the iron exchange membrane. And it will reduce the internal conductivity. So moreover, we choose the revised redox material, and it can driving iron to the migration in the system and at the lower voltage to reduce the energy consumption. And we integrate the renewable energy source like the solar powers, and it can enhance the energy self-sufficiency. Thank you.
I had one question. Right now, you demonstrate for the small system, but for practical application, usually the system is very huge. How to scale up this kind of system? Maybe I think it will be very difficult to scale up.
Yeah. Thank you for your question. So now we have already done the scale up for this system. You can see the bigger system from in here. So we scale up from the around 9 centimeters to the around 800 square centimeters system for the electrical surface area. So we expect that in the future we can maybe introduce our system into maybe like a pilot scale to test its performance. Yeah.
The efficiency will be changed. How to overcome this kind of problem?
Yeah. So one thing is that we can do the like the CFT simulation, like the fluid dynamic simulation, and the other thing is about the system control, like the flow rate and the applied voltage. We can do the test for that. Yeah.
After desalination, is the water drinkable? Can it meet the drinking water standards?
Yeah. So now in our in this study, we can see the decrease of the conductivity of the seawater, but although now it cannot reach the drinking water level, but it shows the potential for the like a wide range of the wide water range. So we can treat like different salinity of the water. Yeah.
Okay, 2 questions. You're talking about the seawater desalination and the carbon capture.
Yes.
From the principle, we have to consider about the selectivity coefficient, ion transport, and others, parameter. Okay, such as volume parameter. Okay, so how do you overcome those barriers? Okay, and secondly, you're talking about the carbon capture. Okay, do you have any data indicate your technology is beyond the technology around the world, or you can compare with them?
Okay, thank you for your question. So first, about the following question, and one is that because we use the redox mediator as our electrode, so it only apply the lower voltage, like below the 1 voltage. So the falling problem will be less concern. And we can also use maybe to increase the flow rate to avoid the falling problem on the membrane. And the other thing is about the compared to the another technologies, like we have compared to our system to the like RO because we have done the seawater desalination. And the energy consumption is like in the similar range, but we can also do the carbon capture simultaneously, carbon capture and seawater desalination. So that's why our system is beyond from the current technologies. Thank you.
All right, time is up. Thank you. Just right on time. We move on to the team number 10.
Testing. Good morning, everyone. So welcome to the demonstration sessions. So we are from the international team number 10, and I'm very excited to be here presenting you our works on the development of a novel upscaling PEC process for the saline sewage treatment coupled with the green hydrogen generations toward net zero carbon emissions. And today we bring two sets of the model for the demo. Here is the batch reactor that we use in our laboratory study, and here is the 1/3 printing model of our newly invented large-size reactor. And sorry, unfortunately, we can't bring the real one here because it's too huge. It's almost the same height as me, but you may refer to the video to have a look. So let's begin from the batch reactor. The primary objective of this batch study is to prove the outstanding performance of our developed PEC technology toward the removal of multiple pollutants and the green hydrogen generations, as well as to comprehensively investigate the mechanism behind those reactions. And during this process, we have successfully developed and synthesized this reduced bismuth vanadate as the photoanode material, which have shown great excellent performance and great reusability during the PEC treatment. And on the basis of this batch reactor, we then make further efforts and develop this first of its kind, a large-size continuous flow PEC reactor operating under the natural sunlight irradiations. So let's look closer. You may see that here's the influent tank, effluent tank, and the pump to control the flow rate. On the upper, it is the electrochemical workstation that we use to apply for the electricity. And here we have the gas sampling port. We collect the gas sample and analyze the generation of greenhouse gases and the green hydrogen. On the top, we have the sun tracking system. On one hand, it can track the sun's position, and moreover, it can allow us to real-time measure and record the light intensity. And here is the control panel for us to adjust the operational parameter. For example, the applied voltage, current, and also the flow rate. Lastly, and also most importantly, is the key component of this reactor, which is our PEC cell. You can see that this cell is totally different from our batch reactor. This is because we are not just simply scaling this one up, but to incorporate many unique and innovative design criteria to maximize the light absorptions on the photoanode, to improve the interactions between the anode and the sewage, and also promote the mixing during the reactions. And during its operations, the sewage will come in from the influent, entering the bottom, and after treatment, it will go out from the top. And here is some water sample that we collected. So as you can see, before treatment is much dirty, and just within 2 hours of the treatment, the water becomes much cleaner. And it's perfectly meet the local discharge standard. And it is well noticed that the direct generation of greenhouse gases is 99% less than those formed in the conventional activated sludge process. Moreover, it generates a significant amount of the green hydrogen during the treatment. So overall, our result has demonstrated that the developed PEC technology is very promising and feasible toward a net zero wastewater treatment. Yeah, thank you very much for listening, and now we'll come to your questions.
Thank you for your work. Okay, two questions. You talk about the wastewater treatment plant. I'm just curious about what type of the waste treatment you use. For example, we have municipal solid waste, municipal sewage treatment plant, and do have some specific industrial waste treatment plant. So do you have tried what type of the wastewater treatment plant you can work, okay? And the secondly, I believe you mentioned about your PEC system is very unique, okay? So I just wonder, do you have going to facing any maintenance problems? How did you overcome that?
Okay, so let's begin from the first questions, which is like pointing about, sorry?
The first question is, can you repeat your first question?
Let me answer. So for this question, actually, we currently using the sewage from municipal sewage, but our technology can also handle the industrial sewage with the chloride concentration higher than 1,000 ppm. We already have our preliminary results from our batch study. This industrial wastewater, including, for example, chemical wastewater, pharmaceutical wastewater, electro wastewater, and also caulking sewage and so on. So our application scenario is actually very large.
My question is that when you scale up, you will have the water management problem. How to deal with this? You had pump water inside the module, right?
Yes.
Now, right now you combine the several modules.
Yes.
Yeah, one who have a big unit, but they still have the water management problem. You had to pump water into the module, but you should have some design about the the water channel. Do you consider that problem?
So, so through our design of the PC cell, we have tried to prevent the water management problem, like the impurities inside the water. Like we fixed the photoanodes on top of the reactor in order to prevent the sunlight, the impurities from blocking the sunlight.
Different channel, the water come in.
Yes. 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 Yes.
They work independently.
Yes.
And
Yes.
this also work independently. So you cannot put the same water go through it.
Yeah, because we utilize the bottom-up flow design to prevent like the dead zones or the water directly coming out without any proper treatment. So, inside our PC cell design, we have already considered the cross-contamination problem or water management problem. Thank you for your question.
All right, thank you very much. Now, ladies, judges, we move on to the booth number 11 right over here. Please follow me. Well, as you know, the next team will do the online presentation, also the online demonstration. We set up a camera right here, so the judges will make a proper position that them can also see you in the other side. So I would like to everyone, judge, please right on here and face our camera. Please move this way. 我们往这边来站一点，哎，好，这边方向能够他可以看到我们所有的人。好 ，OK， 评审委员们，我们这边请。啊，这边不用紧，我们会看着这个镜头，他们也可以看到评审委员们，那我们直接就提问就行了啊。All right, Denmark, are you ready? We are here to receive any information you want to provide. So it's your time. And what's your time? We need to enlarge the volume of the voice.
And also, I take one global version of our product, and it's a hand carry equipment can be used in field application for service. And I'm sorry we cannot demonstrate it on the inside, but we prepared a video and to demonstrate how we can use it. And yes, this is the video. And let me show you. I'm sorry. Yeah, this is the standard version of the driver system, and this is a probe version of our Essence Power, and we just connecting the terminals with the renewable energy systems, and turn on the system, and then we can get to the HLC and the operational state from the system. And then this is the IoT system we developed for the service. And we can, because we have deployed our product in the EV and the wind power and also the PV systems, so we can collect the data, operational data, and the HLC status data from these systems, and we can record this data for the analysis and for the diagnostic and prognostic purposes. And this system will provide the several functions for the user. It included the alarm and the prediction of the remaining useful lifetime. So once the drivers can see the remaining useful lifetime, they can proactive to do the maintenance or replacement, and it could be the more safety and reduce the maintenance cost and the pollution. I think. Yes, this is the IoT system we developed for the Essence Power. Yeah. Do you?
Yeah, I have a question.
Yeah.
In your application in the electric vehicle, you're monitoring the, say, lifetime of your battery. can you show us some real results after your AI processing that when you can detect the malfunctioning or predict the remaining lifetime of your battery?
Of course. Yes, the algorithms have been integrated in the system, and this system just can show the results. For example, the real time, the result after the prediction lifetime, and also if there is an alarm. For example, once one component in the EV will be failures, the failure time will show how long time it will be failure. So this is a remind useful lifetime and provide the information for the drivers that where you need to do the maintenance or replacement. And this is just the system for the EVs, and it's same for the PV and the wind power system. And for the result, I'm not sure, but I think in the proposal we have put some results in the proposal of this project, and yeah, I don't. Yes.
Yeah. Okay. We have two more questions. Okay. One is in your presentation you mentioned about you have two task force. One is for the operation optimization. The other one is called predictive maintenance. Do you have any data in the information can verify this hypothesis?
Sorry?
Do you have real data can present that for your two task force? One is for the system optimization. Secondly is for the predictive maintenance.
Oh, okay. Thanks, Professor. And for the it's sometimes they are the same concept. And for the proactive maintenance, we just provide the remaining useful lifetime for the drivers, and you can decide by yourself where to do the maintenance. This is called this is the meaning of the remaining useful lifetime prediction. And the operational optimization is automatically, because we will provide the healthy and operation status information for the driver itself, and the controller of the driver will adjust its operation conditions to, for example, to reduce the current and the voltages, to reduce their temperature. It's a thermal management, sometimes like the proactive operational optimization. And for the lifetime prediction, it's for the proactive maintenance. There are two concepts, I think.
Yeah, simple question. You detect the turnaround voltage of the power device. My question is there any isolator needed or any additional sensor needed, or you just have a voltage divider for your wider applications?
Yes, it depends on both hardware and the software, and the hardware only connected to the output terminals of the system, and also the software to collect and process the data. Yes, we need both the hardware and the software.
Okay. All right. Thank you very much, Denmark. Thank you for your demonstration and Q&A. Goodbye. All right. We are gonna, the last team of this section is 12. Oh, time's yours.
Okay, this is our zinc air battery, and it's cheap and high energy density and reversibility. Our zinc air battery consists air being cathode, and special hydrogen being electrolyte, and zinc foil being anode. And our battery shell is made by 3D print. And we solve the problem of reversibility of traditional air battery, and also provide a battery that can be used at low temperature. Low temperature, and it's through our special hydrogel electrolyte and nanoscale zinc peroxide catalyst. And lastly, about the integration of zinc air battery. First, we hope our battery can combine with the electric vehicles to create a new hybrid power system. And we hope, second, we hope our zinc air battery can build, can install with the renewable power system like wind or solar power plant. And it can also be integrated with hydrogen production through air blowing. And this can reduce the cost and carbon emissions of hydrogen production. And this is the video we use our zinc air battery that the fan works successful. And the demo today, we are showing the simulation of the application, our battery, which is the combination with the hydrogen production. So we, through our zinc air battery, we let the watch work. And it also can let the LED start. Okay.
This battery, the many people studied a long time ago.
Yeah.
What's the major breakthrough in your study and make this work? Can be the carry out in the industry.
We are different with.
We solved the biggest problem of the traditional battery is the reversibility. So actually, we just solved the reversibility problem through our special hydrogel, because the liquid electrolyte would solidifies and crystallizes easily at low temperature, but the solid electrolyte won't.
So, the biggest challenge for the zinc air battery is people use the liquid-based electrolyte and cannot be charged and discharged, or they can discharge less than 100 cycles, or we say like 100 hours, but we can charge and discharge over 100 cycles. And we use the solid-state hydrogel electrolyte, so even we push the air into the system, the water will not dry out. So for conventional zinc air batteries, because the air, they will dry out the electrolyte, so their life cycle is very short.
When you say 1,000 cycle, does it mean that at what kind of capacity left? Over 80%, 90%?
80%. 80%.
Thank you. Yeah. Do you need any pump? And what is the energy consumption in the pump? Thank you.
Actually, it does not need an air pump. But when you put the air pumping, it will be much efficient. So our next step is to integrate or combine with some high oxygen absorbance material to increase the high efficiency. So for your question, actually it doesn't need an air pump. But our demo is to integrate with the hydrogen electrolysis industrial production and the air pumping system in electric vehicles. And we can put this system in the sustainable energy sectors like solar or wind. So the wind can input the air out in and to charge this battery.
All right, thank you, Team 12, for your demonstration and explanation. Thank you. All right, dear judges, we just complete our morning session. In total, 12 teams complete their work. So the right time is the 12:01. We'll have a short break for the lunch. The next session of the afternoon will be 12:50. So before the 12:50, we will invite you to come back to the same sittings for the afternoon session and judgment. Thank you. 那么现在时间是12:02哦，我们中午休息到12:50。各位呢，随着我们工作人员引导到我们上午用餐的地点。那么下一个场次是12:50。在之前再邀请各位回到我们座位来，12:50啊，谢谢各位。Okay, so now time is 12:50. We're going to have a third section of the presentation. So the following team, we have 4 teams in this section. So at this moment, I would like to invite the next presentation team on the stage. Welcome.
Okay, good afternoon everyone. My name is Rusdan. Here I will present my research with the advisor of Professor Wei Cheng Wang on it. In here, what we are doing is we want to get the net zero emission and then energy transition and of course the renewable energy. So how are we going to do that? Like from agriculture residue and municipal solid waste, we use some system thermal treatment, which is gasification into hydrogen electricity. So here's the model schematic of our system. It's composed to be 3 different system on it, which is the first one is the thermal decomposition. And then the second one is the purification system. And also the last one is high temperature PEM fuel cell. This is our pilot scale of the system, which is the first one, sorry. Okay, oh. Yep, this is the one, thermal treatment, and then CO2 capture, and also fuel cell on it. Okay, from the gasification, we will generate the syngas. From the syngas, the product will be syngas, char, and also the liquid, or we call it condensed tar. And in syngas, we generate 72%, and the carbon conversion efficiency of our system is 76, right there. And then this one is the proximate and ultimate analysis of the tar. After this, I will break down one by one from the main system. Okay, since we do have a syngas and then we want to use it in fuel cell afraid with the CO, we try to oxidize the CO. We change it CO over there with some catalyst on it to be CO2. And we, with the catalyst 37 gram, and then the temperature 120, CO inlet, CO outlet, and the efficiency is right there, 97. So we're able to convert CO to be CO2. And then, since we do have CO2, we capture it CO2. We will use CO2. We can utilize it for CO2 to jet, CO2 to methanation, whatever we want. And we get the purity of the system is 97%. And CO2 recovery, 85.161%. We already changed from CO to be CO2. Now we're going to change H2 to be electricity, which is use a high temperature PM. And with the system power consumption is 24 kilowatt hour, we're able to generate H2, which is hydrogen, to electricity production to be 3.3 kilowatt hour. And here's our comparison with other. There is electrolysis, steam reforming, and other. And here is our system. We call it decarbonizer, which is this one, and this is the pilot scale on it. And decarbonizer, we call it blue hydrogen, right here. With the energy consumption of 0.2 megajoule, and then H2 production is 11.5, carbon emission is 0.01. Why the emission is quite low? Because we capture the CO2, and then we purify the hydrogen as well. So the efficiency of whole system of this is 79% on it. And here is the environmental analysis, which is talk about the carbon emission. How we calculate the carbon emission, mentioned on this slide. Okay, we do have a feedstock. Feedstock is come from the transportation. How long the truck will be drive the feedstock from feedstock to be our system. So for example, we put in 8.78, then we get the carbon emission 5.71. And also our system. And then this is the how many kilowatt hour we generate from the system. So in total, the CO2 equivalent on the system is 19.95. And here's the overall result on it. Like based on 10 kilogram of feedstock, we can capture that much. We can CO2 emission reduce, like because we use carbon capture system, we get 13.71. And then since we are generating the electricity from fuel cell, we're able to feed back the electricity recovery, which is 12% on it. Yep. And this is the future perspective. Our system already work all of them, like including 3 systems, thermal decomposition, CO2 capture, and fuel cell. But this is not done yet. Like there is a lot of things we still can work on it. In terms of energy, we can use energy efficiency, pinch analysis, TEA, and then exergy, we can use exergy flow, exergy efficiency, and cost destruction. And then the economy, we can minimize the H2 production and maximize the product credit. And also the environment, we can calculate the carbon intensity, and also other potential pollution to achieve sustainability. Thank you.
Thank you. Thank you, team number 13. Now we are moving on to the team number 14. Is your time.
Hello. So hello everyone, we are a team from National Taiwan University, and our project is to use the civil afforestation to, enhance the ocean carbon dioxide sequestration in the deep ocean. So let's begin with the first questions. Why do we need carbon dioxide removal technique? So the answer is given that the current level of this current atmospheric carbon dioxide and the future projection, limiting the global temperature rise to 1.5 degree or well below 2 degree will require CDR, as clearly stated by this IPCC 6 assessment report. However, to achieve this, we need to find a large carbon storage for this, large carbon reservoir for storage. And we need to find a technique that can be scaled up. So this brings us to the second question. Why the ocean is important in this whole picture? So scientists have known this over 50 years now, that the ocean, especially the deep ocean, can store large amount of carbon up to 1,000 years. So in fact, the deep ocean is the largest carbon reservoir in the surface of the planet. So it holds roughly 15 times more than the land plants and 50 times more than the carbon dioxide in the atmosphere. So most of the carbon stored in this deep ocean through a process called biological pump. So the carbon dioxide is fixed by the marine phytoplankton that living and photosynthesizing on the surface of the ocean. And part of the carbon is transported into the deep ocean through sinking. And they will be decomposed back to carbon dioxide by the marine microbes. However, due to the slow mixing between this surface ocean and also the deep ocean, the carbon is efficiently stored in this deep ocean up to 1,000 years. That they will need a longer time, up to 1,000 years, to be returned back to the surface ocean. So to enlarge this deep ocean carbon storage within a short period of time, we need to find the plankton that can fix more carbon dioxide and sink more quickly to the deep ocean. And the solution may lie with seaweed. So seaweed has several great advantages for this carbon sequestration. So first of all, unlike other land plants or seagrass, they can grow on any floating surface, making them scalable to this open ocean. And then comparing to other marine phytoplankton, they have higher nutrient use efficiency and a higher sinking rate, making them could actually take up more carbon dioxide and sink more quickly to the deep ocean. So although seaweed afforestation may potentially upscale to all open ocean region, it is particularly interesting for Taiwan. Taiwan is an island that's surrounded by vast amount of ocean water, and half of its territory actually extending into the sea. So nearly 20% of the Taiwan's water lies in the deep water deeper than these 500 meters, and this deep water is very important for storing carbon dioxide. So comparing to other countries such as the United States, that Taiwan has a greater potential to use its territory water to remove and store carbon dioxide. Furthermore, Taiwan has over 600 natural species of seaweed, and most of them are fast-growing tropical or subtropical species. So since October, we have set up a 300 meters square of this offshore seaweed farm off coast in Taitung and near the steep slopes that leads to the deep ocean basin in the Pacific. And this is the first offshore seaweed farm in Taiwan and among the few farms that set along this continental slope. So our farm currently growing 120 kilograms of seaweed, and it has been tested through this winter monsoon and the most recent super typhoon Gami that actually proved its resilience. So we apply multiple monitoring systems to estimate the growth rate of the seaweed, their sinking, and also the carbon flux. So this actually includes the seawater sampling for the subsequent analysis for the nutrients availability and the changes in this carbon chemistry. Sensors also for the continuous monitoring of the physical and the chemical properties of seawater, including temperature, salinity, pH, PCO2, chlorophyll, and the dissolved oxygen concentration. We also apply underwater acoustic sensors to constrain the sinking and the direction and the sinking speed of this water current, as well as the sinking material from the seaweed farm. Video and those camera systems. So we deployed net traps that are designed by our groups to collect those sinking material in order to quantify our sinking carbon flux. However, in parallel with our field observation, we also conduct incubation experiment in the laboratory, trying to understand how these environmental conditions, such as the nutrients and light, control the seaweed growth, and how this seaweed decompose in the dark. So our study has shown that seaweed farming in the offshore waters is scalable and is a natural solution to sequester carbon dioxide in the deep ocean by leveraging Taiwan's unique geographical advantage. And by using just 10% of Taiwan's territory water for seaweed cultivation, it could sequester up to 2.6 million carbon dioxide annually. And this is equivalent to 1% of Taiwan's total emission. So besides removing this carbon dioxide using the seaweed farm, our seaweed farm has also significantly increased the fish population and the ecosystem diversity. So this technique is environmental friendly and can be integrated with other marine business such as the fisheries and aquaculture. So, and this is our team, and thank you for listening.
Thank you, team number 14. Now we're moving on to the team 15 with your presentation on the stage, please.
Okay, hello. I'm here to present an ultra-high efficient bidirectional DC to DC converter. Which one? This one. Okay, okay. So first I'm going to start with the global electricity generation. Per year is around 30,000 terawatt hour. And we also know that a conventional 500 megawatt coal power plant can generate around 3 terawatt hour per year. That will mean that if we were to improve the efficiency by 1% in the energy generation, we could potentially be saving around 100 coal power plants. Of course, this will help reduce the carbon emissions. Also, in this chart, you can see what the efficiency is for several EV battery chargers from different companies and different power ranges. Most of them peak at around 95%. The goal of our team is to have this efficiency much higher than 99% by means of using wide bandgap devices. So this is the topology that we're proposing. You can see at the right top side is the prototype that we have developed. It's very compact. And on the right bottom side is the topology, which is based on a dual phase interleaf buck. And it will be supplying power to a battery from a DC bus that will be provided either from conventional energy sources or renewable energies. The goal is to have in the future just using directly the renewable energies to the DC bus and our proposed technology to supply power to the battery. Also, we have developed a controller. The controller is based on 2 stages. The first stage is just a simple PI controller that controls the voltage and current flowing to the battery. And the second stage is very important. It's a precise ZVS calculator. What it does is regulate the switching frequency so that the converter works under ZVS operation and eliminating the switching losses. So the basic structure of this controller is to, at the first blue spot there, we generate a dead time. During that dead time, the negative current flowing through the inductor will help us discharge the output capacitance of the device, this pink one. And exactly at the time when it's 0, we will turn on again the signal so we can continue with the switching operation. And at that instant, at the second blue point, the power dissipation will be equal to 0 because there is no voltage there. And this has been also proven in experimental waveform at the right side of the screen. And to test this, we have tested it in a back-to-back configuration. So we are actually connected 2 similar converters, one working as a boost and the other one working as a buck. And we let circulate the main power between them. And this allows us to have a highly precise efficiency measurements. And with the measurements that we had made, here we have the experimental results at 1.1 kV in the bus and 6 voltage at the charging of the battery. And you can see at the negative point of these inductor currents, the blue and the light blue ones, is where we reach the ZVS. And you can also see the gate and output capacitance voltages there at the right side for both phases. As you know, this converter has 2 phases, so both phases have ZVS operation, potentially eliminating all the switching losses, and also works at high frequency. This frequency here is 360 kilohertz. That also allows to reduce the magnetic components of the converter and also reduce the total size and weight of our converter. So we have measured the efficiency, and you can see that the majority of the efficiency falls beyond 99%. One of the specific points that we have there is at 99.82% efficient, transferring 15 kilowatts of power and at the output of 1 kilovolts. So the broad benefit is that in the future, in 2050, we will have a projection of a large increase in the production of green energies, mainly solar, and solar is very unpredictable, so we will need a way to store it. So, for example, if we have the improvement of 5% using our converter, we could potentially, for energy storage system, we could eliminate 160 coal-fired plants. In the case of EV charging systems, we will be saving around
16 fire coal plants. So we have successfully developed this bidirectional DC to DC converter highly efficient, and we can potentially eliminate 176 fire coal plants worldwide. Thank you.
Thank you, 15. Now we are going to have a next team. That would be the fourth one at this section. Now, number 16, please come onto the stage. After the team number 16, we'll move on to the booth to observe their demonstration. So now is your time. Go.
Good afternoon, panelists of the jury and all other members of the audience. We are from the University of Mertua, Department of Chemical and Process Engineering, and we are here to present to you our project on ecoalgae transforming waste into wealth. Let's start off with the problem that we identified. The problem is that agricultural wastewater treatment is expensive. And secondly, it's a potent source of surface water contamination. Agricultural wastewater, in order to be purified, to be released safely, requires multiple stages of treatment. The first two stages, to remove suspended solids and dissolved solids, are relatively cheap. Those aren't a problem. The problem comes about when you want to remove the inorganic ions present in the agricultural runoff, things such as heavy metal ions, things such as nitrates and phosphates. The existing methods to remove this, things such as reverse osmosis or nanofiltration, are extremely expensive. And in order to run these cheaply, you need to rely on energy produced using fossil fuels. You have cheaper methods like chemical precipitation and adsorption, but those create new waste problems. You need to dispose of the precipitate or the adsorbent at the end of the day. What were the observations that we made regarding this problem? Firstly, you have a problem where farms do not treat their agricultural runoff. They dispose of the pure agricultural runoff directly into tanks and reservoirs, meaning that you contaminate the domestic water supply. But in addition to that, we observe problems like eutrophication, where these nutrients lead to algal blooms that overgrow in and dominate these freshwater ecosystems, destroying all other forms of freshwater life. This leads us to the concept development. We wanted to figure out whether the challenges present in chemical and physical methods of tertiary wastewater treatment can be addressed using biological methods. And that's where we came across algae. Microalgae is capable of using phosphates and nitrates for their growth, but they also grow rapidly and they can be found almost anywhere, meaning that it's easy for farmers to acquire and use. Growing microalgae is also good for the environment because they perform photosynthesis and perform the direct carbon capture from the air. After identifying this concept, we needed to focus on the viability of using algae for wastewater treatment. It's very well established in the scientific literature, and our experiments also show that you can have phosphate removal rates of 75% and nitrate removal rates of 87%. The microalgae also has the potential to remove heavy metal ions, such as nickel, copper, and cadmium to an appreciable extent. Since they grow through photosynthesis, they perform the direct air carbon capture while generating oxygen. The ultimate benefit of this is that your energy requirements and chemical requirements are far lower, meaning that you have an 85% cost reduction in many of these cases on average. But the cost reductions don't end there. Because ultimately, what you gain at the end of the water treatment process, the algal mass that you get at the end doesn't go directly to the landfill. This can be used to create further value-added products. And the product that we identified is biofuels. The biofuel yield that you get from algae is much higher than other plant oils, like peanut oil, for example. On average, you can get about 17 grams of lipids from 100 grams of algae. These lipids can then be reacted with methanol to create biofuels, which are drop-in fuels, meaning you don't need to modify standard engines. You can drop it in directly into an existing diesel engine, meaning that now you have a net zero type of carbon fuel to be used on the farm as well. The algae also has the capacity to have a carbon capture efficiency that's 50 times higher than terrestrial plants, and they produce about 280 tons of dry biomass per hectare per year, absorbing 513 tons of carbon dioxide. These numbers are good, but they could be better. The existing systems that you have to grow algae are open ponds. There are a few problems with open ponds. Firstly, you have a poor growth rate, which means that the residence time of the wastewater is really, really high, and therefore it's not necessarily very efficient. But also, the microalgae can die due to climate fluctuations and contaminations as well. These problems can be addressed using photobioreactors, but those are expensive to produce, expensive to operate, and nearly impossible to scale up to the level that you want in an agricultural setting. Our proposal then is to enhance the open pond system. We have a few levels of enhancement. Firstly, we have direct carbon dioxide diffusion into the agricultural wastewater. The carbon dioxide that we diffuse into the wastewater can be emissions from the agricultural system itself, and these diffusions will be used to maintain a constant rate of carbon dioxide within the open pond. Furthermore, we have greenhouse covers to maintain the temperature to ensure that it does not drop below a certain value and kill the algae in the process. We have thermal insulation to be used at night to ensure that the heat does not escape. And we propose an experiment with disinfectants to ensure that the contamination is minimized. Ultimately, the expected benefits of this process are massive. A 15 million gallon per day wastewater treatment plant can have annual costs of up to $21.9 million. Similar open pond systems where you grow algae can be operated annually at a cost of just $2 million. You have such a significant reduction just there. But the production of biofuels further offsets this cost, making it even lower, meaning that our process is not only good for the environment, but good for the farmers as well. The final benefit then that I want you to focus on is on the reuse of treated wastewater for irrigation instead of just releasing it into the water supply, meaning that you can meet your water conservation goals as well. Keeping all this in mind, we hope to see you at our booth. Thank you.
All right, thank you, 16. Okay, now judges, I would like to invite you to move along to our next booth because this time we have 4 teams as one section. So now let's go to the team number 13 to observe their demonstration and explanation. This way, please.
Yeah, okay. So here is our system. In here, as I said in the stage, we do have a thermal decomposition, we do have hydrogen purification, and also fuel cell. So how it's work is we generate hydrogen from here, and then we purify in here, and then we also capture the CO2 in this device, and then we store it in this. We can utilize it for, we can sell it, or we can further utilization on it. And then since in here CO2 and H2 already in here, we do have a problem with CO because CO is not good for fuel cell. We use CO oxidizer to generate CO to be CO2. Then we capture in here. Then the gas came here is only hydrogen. And we generate electricity on it. And here is the pilot plan. And based on these 3, we are going to have some, yeah, we already tested as well. We are going to have some spin-off company on it, which is this one. And our target is not only agriculture waste, but we also able to use industrial slurry. And we can just move it, because see in here, we can just plug in it in an industrial park or some company on it. If they want to deal with some waste on it, we just bring our system to the industry, which is we already tested, and they can deal the waste inside of their company on it. And yep, so here's the animation of the thermal decomposition. See, we generate. And another thing I forget to mention in there, we do have a plasma. As I mentioned in the PPT, we do have a long chain of char. Char is difficult to change it. Char is like a liquid, and on that liquid, we analyze it in GCMS. There is a long chain hydrocarbon on it. And how we gonna break down that long chain hydrocarbon? because we want to generate more hydrogen on it. So we use a plasma. We use plasma right here, the bottom part, which is this one. We generate a plasma in here. So we add a plasma to break down the long chain hydrocarbon on it. Then we can get more hydrogen or carbon. Then we use it in this system. Then the last part is the hydrogen from electricity. And the data in here is, this is based on 10 kilogram. This is the data based on 10 kilogram. We can go for higher, 20 kilogram and 30 kilogram. And then we're able to capture, CO2 capture is 11.65. And then the total electricity consumption in here is 24.17 kilowatt hour, which is quite low. And we get the electricity from fuel cell is 3.31, which is not that high. We are going to make it higher with a lot of way on it. And we can get a recovery 12.04% on it. That's all from my.
How do you treat the sludge, which is liquid, right, with the plasma?
Okay, if we want to use an industrial slurry or sludge, we will feeding it from here. We will feeding the sludge from here, and then we burn it. And then, you know, sludge is a liquid. And we do have a cyclone as well. It's not mentioned in here. Probably in here. Yeah, we do have a cyclone. This is a plasma. We do have a cyclone in here. And in that cyclone, we collect the industrial slurry first. So if there is a like byproduct of the slurry, they will store it in that place. And then another syngas will goes to the plasma, long chain hydrocarbon, we break down, and then we generate more hydrogen or carbon on it, something like that.
Yeah. I can see you benefit for the waste reduction and the hydrogen production, but I'm curious about how about for your carbon reduction? Okay. And secondly, do you need any air pollution control to treat all air pollutant? Air pollution control. The last one, do you do any life cycle assessment?
Okay, then that part is on here. So for the pollution control, see in here with CO2 capture. So we capture the CO2 on it. So we capture CO2. We don't need to how to say like okay.
Particular metal.
Okay. NOx and SOx. NOx and SOx. If we running industrial slurry, there is NOx and SOx, yes, right. And NOx and SOx, we can use another catalyst type. How we gonna make that one? Okay, there is a char from here. And the char, we do some another treatment on it. And from that treatment, we use it for make it like activated carbon or some filter on it. So we can like say disconnect, like not disconnect, like separate the NOx and SOx on it. Something like that.
Yeah, I think you need to provide the additional air pollution control device. Okay, and the secondary, I think for the entire system, you talk about this is a comprehensive solution. You have to do further life cycle assessment, okay, to achieve your goal.
Okay, but actually life cycle assessment already in environmental analysis on it. There is calculation on it. Yeah, by the way, thank you. Thank you.
All right, thank you, 13. Now we're moving on to 14. There are 6 minutes, including the demo and Q&A. Please.
Hello, everyone. We're group 14, and our project is try to using the advantage of the seaweed to absorb the carbon dioxide from the atmosphere, and then that is sink into the deep ocean depth, which it can store up to 100 to 1,000 years in the seawater. So we are currently growing 120 kilograms of seaweed in the total area of 300 square meters seaweed farm off the coast of Taiwan. So this is our small model of the seaweed farm, and we cultivate three common seaweed species, which is Eucuma and Sarcodia and Ovar an ova in the tube net. So the ability for a seaweed to absorb the carbon dioxide from the atmosphere is based on this growth rate and also its nutrient availability in the seawater. So the most importantly is how we are going to quantify this parameter by this equipment in the underwater. So the first is the underwater acoustic current profiler, which we can measure the vertical and the horizontal current movement and the particle sinking. And the second is an underwater video camera, and the third one is the CTD, which we can measure the salinity and temperature and also depth and it also has the pH meter sensor attached on this, so we can quantify and know the chemical properties of the seawater. And the last one is we also put the net trap under the seaweed farm to quantify the sinking carbon flux. Thank you.
Thank you for your presentation. I know we have lots of seaweed around the world. My question is why you choose this 3-1, okay? Secondly, in order to protect the ecosystem or the marine system, sometimes we have to care about the nutrient cycle, water cycle, and the carbon cycle. So I wonder, did you develop any model which you can predict what will be the outcome, especially for the environmental concerns?
So the reason we choose these 3 types of seaweed is basically it's very common, and also like we choose the red algae for Sarcodia and also Eucuma. It's because it can use the asexual reproduction, so it can just grow continually during the year. And also for the nutrient cycle questions is actually different types of seaweed has a different carbon to nitrogen ratio, but also because the carbon to nitrogen ratio of the seaweed is way more higher than the phytoplankton and other organism in the seawater. Which is if the organism seaweed has a higher carbon to nitrogen ratio, then it can use a small nutrient, which is inorganic nutrient, and to absorb large quantities of the carbon.
How do you resolve the issue of competition with the fishery for the ocean space?
Yeah.
So far,
maybe, yeah, I can try. So far, we also, because we have the underwater video camera, so we also catch the screenshots and also the video of the fish. They are actually eating those seaweed. So it's kind of like the coexistence in this habitat. So I think
just to add that we actually collaborate with local fishermen for this experiment, and they are very happy for us to do the experiment because apparently our farm trapped a lot of fish, and they definitely like this.
Yeah, thank you.
You only capture 1% of the carbon from Taiwan, and you need 10% of the space. So it's a lot.
Yeah, well, it really depends because right now we don't have any other technology to remove carbon dioxide from the atmosphere. The only one available technology is air capture, and that actually also costs significantly more than what our seaweed farm currently costs. So it comes to the cost, and then the other thing is that the seaweed farm can actually be scaled to the open ocean. It doesn't have to be limited to the territorial water. Right, so there are 78% of the Earth's surface is covered by ocean. So potentially they can all be used for this.
Okay. All right, any other one? All right, thank you. Thank you, 14. Now we move on to team 15.
Hello. Hello, everyone. So what we have here is that we have designed a ultra-high efficiency bidirectional DC to DC converter.
The reason of doing this is because we have there is a projection by 2050. You can see in the first graph there, the green energy generation will come out of the bulk of the total generation will be green energy. Most of it is going to be solar. So we know that solar is very unpredictable, especially during the day. Some times of the day is when it generates more the power. So for sure we will need energy storage systems, and that's one of the motivations to use this. And we wanted to have a converter that has really high efficiency and potentially reduce the losses and reduce the carbon footprint by then. The converter itself is here. I have three equal units here, and it's based of what I have here. First of all, is a 15 kilowatt converter. The output can go from 150 volts to 1 kilovolt. So you can see that it's very compact. And we use silicon carbide MOSFETs, which are wide bandgap devices. And together with a smart controller that we have implemented, we can reduce the losses, increase the efficiency, and also reduce the size of the magnetic components. So that's why you can see that it's very compact. The topology is right there. Is dual bug interleaved, and what this topology does, or it needs, if you see the triangular waveforms. Thank you. Where? This one? Oh, sure. Thank you. If you see the triangular waveforms, we need each of these inductors to go to a negative value. It's a very tiny negative value. It shouldn't go so negative. A very tiny negative value so that we can discharge the output capacitances before we activate the gate signals, so that the switching loss is eliminated. Oh, sure. And we have tested this converter in our lab up to 15 kilowatts, and we have reached always above 99%, and at the 1 kilovolt condition, that is this case, we have reached 99.8%. It's very highly efficient at 15 kilowatts of power transfer. And we also have recreated the experimental waveforms here, right here, but because of the power limiting conditions of here, we have tested at only 1.5 kilowatts. So you will see a little slightly lower efficiency. This is around 99% efficiency at 1.6 kilowatts. And you can see the signals, the output capacitance voltage discharges right before the yellow gate signal activates. So that means that we have 0 voltage switch in one of the phases. Actually in both phases, but we're just showing one of them. Yeah, and that basically is. And if you want to grab one of these and observe them in detail, you're free to get one of these. There is another one here. Thank you.
Yeah, congratulations on your high efficiency achievement. Could you please talk about the adaptive daytime tuning mechanism first time, and second time we did work under light load condition. You showed efficiency only about 150 watt. How about that? Less than that, 150. Will it work? Yeah. Thank you.
Yeah. So we use a fixed dead time. We calculate that dead time to be for this converter around 200 nanoseconds. And based on that dead time, our computation measures the input DC bus voltage, the battery voltage, the current flowing, and also we need to know the inductance that we have here, and our controller will compute the switching frequency at which we need to operate to achieve ZVS, to achieve those waveforms that you see there, like discharge and then activate the signal. It works for all the load range with no problem, and with that, that's what our controller does.
Your calculation depend on the COSS of the silicon carbide.
That's right. That's right. It depends. We have the, we can say like a lookup table of what the COSS is at the particular voltage. So yes, it does.
High power range for this device.
The power range?
Yeah, right.
Well, it's...
You mentioned, according to your presentation, you mentioned it's good for the very wide range of the
Sure. Those experiments there are for 15 kilowatts. As you can see, they're okay.
How about the
and
high
we have
power?
repeated that at a really low power range. That's the high range, and this is the low range. So for both cases, yeah.
Continue my question. You mentioned you need the lookup table, but actually, as the DC voltage change, the COSS change.
Right.
So you have a multi-dimensional lookup table.
Right. We have for a specific COSS value for every region of the voltages, so that we can make more accurate calculations. Yes.
Yeah. Great. Appreciate it.
Right.
Yeah.
Thank you.
All right. Thank you. Thank you. Moving on. Moving on. Right over this way. This is the last one to do the demonstration before the short break.
Okay, hello everyone. So this is the unit that we are using. This is the enhanced open pond system. So as you can see, here is our carbon dioxide injection system. This is just a setup that we have for this. Our main goal is to actually use agricultural emissions for this. So if you come closer, you can see that the carbon dioxide is being bubbled directly into the water over here. Aside from that, this is the greenhouse cover that we have. This traps in the heat that you get from sunlight without letting it escape. At night, we will be putting on a further reflective cover. And what that does is it just traps the heat in without letting it escape. There should be covers at the front as well. Due to the air line, we couldn't have all of that. The reason we have a paddle wheel over here is to make sure that the water is rotated all around so that the algae doesn't stagnate or go to the bottom of the pond or anything of the sort, to make sure that there's an even distribution of nutrients. The way that we are currently operating this is that we are taking batches of wastewater and then we are growing the algae in that over a period of about a week. And one of the other reasons that I want to highlight as to why growing algae in wastewater is so good is because actually the lipid content of algae is higher when you grow it in wastewater due to the higher nutrients as opposed to freshwater. I think that covers everything for our demonstration. If there are any questions, we would like to welcome those.
Yeah, you know, this is the turbine, okay? It's the mixer. Do you know the function for this mixer?
The what?
Yeah, the function for this generator.
Yes, so we rotate the algae to make sure. All right, so we rotate the water to make sure that the algae doesn't stagnate. And the reason you don't want it to stagnate is you can have like high concentrations of oxygen or carbon dioxide or the nutrients in one particular area. And then that high concentration can reduce the efficiency or just kill the algae outright.
Yeah, another reason is you have to make sure it's homogeneous. You know, you need to have a mixing, so you know the mixing intensity, okay? Mixing intensity. So you have to ensure all the water quality and the liquid, okay, that's a homogeneous solution there, right? And provide some reasonable oxygen in there. So do you do any calculation to make sure this is the optimum operation stages?
So the mixer actually operates at a slower rate. This is something that we had to bring with us to bring it here. So the reason we have the mixer needs to be a bit slower because the algae can die if it's too fast. We've done calculations regarding that. Regarding the nutrient levels and the homogeneity, actually we are taking direct wastewater because if we add more nutrients, that just doesn't solve the problem, right? Because so the nutrient isn't controlled. We are taking wastewater and growing algae within it. Aside from that, there are like no more other calculations. The carbon dioxide diffusion, we've done calculations regarding the optimum carbon content, carbon concentration that you need to have in the water, and that's what this is for, to maintain that.
to get the lipid from the microalgae, you need to break the cell wall. The cell wall can take a lot of energy to break, and it also needs some extra energy to extract the lipid. So what's the percentage of those kind of consumption, energy consumption?
We still haven't done this at like the large pilot scale. This is still the lab scale of experiments, so we haven't done the considerations with regards to the energy of the blending or the pressing that might be required. Anyway, the main goal is not to have like fully efficient lipid or fuel extraction. The main goal is to reduce the costs through the algae, and we'll offset those costs by producing the biofuels from the lipids.
Carbon credit. Is there a potential to get a carbon credit, or have you established the MRV for the system? Carbon credit, I think this is a good way to obtain the carbon credit from your government or from the nation, from the UN.
All right, so our government, they don't have the carbon credit system, so that's a bit unfortunate.
Carbon credit from the United Nations.
I see.
Okay, but first you need to establish the MRV system.
All right. Okay. Now, the judges, we just complete our demonstration at this moment, so we have a short time to take a short break. So the next session will start at 49. It's about 10 minutes away. So we have a 10 minutes short break. You can take your seats and enjoy your break.好，各位评审委员，我们现在时间是40分啊，我们休息大概9分钟左右到10分钟啊，下一个阶段大概在49分，我们会正式再进行下一个阶段，也就是最后一个阶段，4个团队，谢谢。We have 1 minute to our last section. It will be starting by the next presentation team, number 17. So please stand by.
This.
Okay, now let's start. So welcome, number 17 on the stage.
Hello, Dylan. Hi, Ganesh. Have you ever thought about how much energy libraries use to power its lighting needs? Well, it turns out electricity represents around 40 to 50% of the total energy used in buildings.
Well, why not just maximize natural light to actually reduce artificial lighting?
Well, simply because too much sunlight can lead to excessive heat, hence increasing the cooling load.
Well, now that's quite a challenge. How can we balance sufficient lighting, energy conservation, and avoid excessive heat? Is it actually possible?
Yes, it is possible because our design, Dresdanta, a net zero public library in Sao Paulo, tried to address the 3 main problems holistically instead of using standalone technology, ensuring both thermal and visual comfort for reading while achieving net zero energy and emission status through the use of these passive and active strategies.
Impressive, but before we continue, we need to understand the context first, right? Why Sao Paulo? Sao Paulo is the largest city in Brazil with a literacy rate of 99%. With that, a net zero public library is proposed to support it. Sao Paulo is classified as a hot and humid subtropical climate with temperatures ranging from 19 to 28 degrees Celsius. And through a windrows analysis, wind could be potential for passive cooling strategies.
That's very true. Now let's actually delve into Dresdanta. For starters, based on our analysis, the baseline energy needed for cooling load is 3.5 million kilowatt hours, which is a lot of energy. So what do you think we should do?
Well, if I were you, first, we optimize the building's orientations. Through parametric optimizations, 10 degree is found to be the most optimum orientations to minimize radiation, maintain daylighting, and maximize natural wind from the southeast. This orientation is then supported by Dresdanta external envelope, which consists of 5 different facades on different sides. We measure the sun shades through the calculations of sun altitudes and azimuth angle to adapt to the summer and winter solstice. Let's zoom in. In the northern area, we use canopies, and at the southeast and southwest, we use vertical fins. Calculations are shown in the slide. As such, summer sun is blocked while winter sun is let through, hence letting enough daylight to the inside of the building while avoiding excess heat gain.
Oh, I totally agree. This approach cuts the usage of artificial lighting and HVAC, reducing energy use by 18.61%. Now moving on to our next strategy, I have an idea. In the middle of Drestanta is a pond and reading amphitheater which uses wind as a passive cooling. So we have a pond, but how do we actually incorporate wind to be able to work together with the pond? Now the south facade features a crisscross tapered brick design that optimizes wind velocity, which allows evaporative cooling, stack effect, and cross ventilation to all happen, hence creating a comfortable reading area. But the question is, how did we actually treat the facade to be able to do such effects?
Instead of using regular box bricks, the bricks are angled to become tapered angle. The selected range of result is 25.1 degrees at the southeast to 26.3 degrees further to the south and the east. And then a 3x3 module part of the building is then simulated to optimize the taper angle. The selected range of angle will provide a comfortable indoor wind movement.
Now, that's right. This strategy reduces the HVAC area coverage by 261 square meter, hence reducing energy demand by 12.5%. Next, we will delve into the thermal mass design. Both exterior and interior layers are designed to be low carbon, which are all designed to have optimal U values and SDC values, so that it has optimal heat transfer and also soundproofing.
Low carbon, net zero emission.
That's right, passive approach. Now furthermore, the west side incorporates vegetation as a heat buffer.
Yes, with a total green area of 3,400 square meters, the building is capable of absorbing that amount of carbon dioxide annually and producing about the same amount of oxygen. This strategy contributes to reducing energy usage by 21.36%.
But wait, are we stopping there? No.
Up until now, the three strategies have the potential to reduce cooling load by 52.4%. Our analysis shows the incoming light from our passive strategies complies with the human eye's comfortable level of 200 to 500 lux.
But are we stopping there? No. No. Yes, of course not. Nice. Moving on to the active system. Potentially, in Sao Paulo, we could utilize ground source heat pumps, which harnesses the Earth's temperature for efficient heating and also cooling. The system uses ammonia and water for indirect cooling system for high efficiency and zero global warming potential. The ground source heat pump integrates seamlessly into buildings, offering low noise and reduced energy use. Our active system also complements with the humidifiers, positive pressure, and air filtration to create comfortable indoor condition.
How effective?
Well, this strategy cuts the energy usage for compressors, thus reducing energy demand by 23.25%.
So far, we have reduced energy use by 75.65%. Thus, to actually achieve a net zero status, we use solar PV systems as our renewable energy source. Sao Paulo has a remarkable solar radiation potential, so we utilize most of the roof area for PV panels. We use raised mounting system for passive cooling, inspired by the agrivoltaic method. With our parametric tilt angles, we can obtain more than 1 billion kilowatt per hour from solar energy alone. This strategy provides an additional energy of 21.61%, resulting in a 4.36% surplus of energy in summer and achieving overall net zero energy with an annual calculation.
Okay, I think we're done for the net zero energies. Now for emissions, Drestanta achieved a 142 CO2 per square meter, achieving great air rating and a gold rating in elite score. Thank you all for your attention. We invite you to go to our booth and then go for more detailed information about our innovations. Thank you very much.
Thank you so much for number 17 for your presentation. Now that's waiting for number 18 to go on to the stage to present. Let's welcome number 18.
Check, check. Oh, this is for next. This one for forward then? Yeah. Okay.
Good afternoon to our respected jury, TechCo Foundation, and everyone that have been here. We, International 18, will present you an Bromelite library and share our ideas about how to make net zero building from green building. Next. So, but why we choose green building? Did you know that there's a significant share of carbon emissions from the built environment up to 42%? This means green building practice are essential for sustainability. These are 5 keys of green building that are functional, operational, environmental, management, and financial. Next. First, the project based on the site located in Sao Paulo, Brazil, that is located in Centro. This place has significant value of cultural and branding district. But there are problems where Centro has a high carbon emission and abundance from the construction materials such as concrete and brick. Then we try to analyze the climate, where the climate has hot, humid, high precipitation, high humidity up to 80%, and high abundance of solar radiance. Next. Then we compose 6 strategies of the building, the solar radiation, humidity and rainwater response, indoor environmental quality, energy efficiency, low carbon strategy, and financial strategy.
Next. For humidity and rainwater response, we use water collector facade. Besides bromeliads plants as green walls, we use foliature facade shape. The facade can collect up to 800,000 liter per year. Next. Our research begin. We start with capturing water in Sao Paulo. Next, we research about our optimal mesh that can be used. Next, in terracotta facade, we use implementing terracotta clay.
We use terracotta facade to preventing the solar radiance, and it has 31 more efficient. Next.
So for the active strategies, we are focused on the MAP system, right? So firstly, the efficiency system is based on the climate. As we can see from our simulation, cooling become the main concern of the efficiency system. Therefore, must be the main focus of our efficiency system. And also the function of the library itself, as a public library, have many rooms that produces heats, such as server rooms and mechanical system rooms, which can be used for other rooms. Therefore, we chosen the VRF with heat recovery system to use this opportunity, and also use R32 refrigerant, which are more greener, resulting in these advantages. And also in making sure that the humidity is suitable for a library, and also preventing COVID spread, we also use a couple measures such as a liquid desiccants, DCV controlled air handling unit, and portable HEPA filter unit to achieve energy efficiency while also ensuring good indoor air quality. And lastly, next for the lighting system, we also use a novel strategy in planning or the demand of the lighting of the building by using a space-to-space method, which we define each room lighting needs compared to a whole building. And also for the operational strategy, we use an LED compared to fluorescent, daylight sensing, and occupancy sensing, achieving 66% decrease in energy, in operational energy. Next.
Okay, next, we also optimize the water management strategy using these 5 strategies: rainwater harvesting, native vegetation landscapes, efficient fixtures, fog harvesting, and grey water recycling and reclamation. After we implement these 5 strategies, a simulation in Green Building Studio show a 67% reduction in water usage in the building. saving 9 million water liter per year. Next. So how we achieve a net zero? First, we categorize the load in our building energy consumption into 5 categories: heating, cooling, water pump, lighting, and room electricity. In the baseline case, the EUI, the energy use intensity, was 200 kilowatt-hour per meter square. After we implement both passive and active strategies, we managed to reduce the EUI into a 59% reduction. And to further achieve the net zero energy building, we also utilize a solar PV as our renewable energy resource. To conclude, ladies and gentlemen, our bromelated library project set an example for our building system, a sustainable building system, which both integrate both passive and active strategies, and also we implement a sustainable mechanical system to reduce energy consumption. Thank you.
Thank you so much for 18's presentation. Now we are welcome for the next team.
Test.
Now we welcome 19 for the go on to the stage for a presentation.
Hello everyone, we are the process system engineer from National Taiwan University. We are going to propose an practical energy transition strategy for Taiwan to meet the sustainable future. Recently, more than 90% of the primary energy required in Taiwan is imported, and more than 86% are fossil fuel. To meet the net zero carbon emissions targets, Taiwan should reduce the importations of the fossil fuel and ramping up the production of local renewable energy. However, Taiwan's limited lands and high population density make it challenging to produce sufficient renewable energy locally. Therefore, we propose an international renewable energy supply chain to ship the renewable energy from the energy-rich regions to Taiwan. The first scenario is to store the green electricity in the lithium battery, and the lithium battery can send to Taiwan. And the second scenario is to send in the form of the hydrogens. The green electricity in the exporting country can convert it into hydrogens via water electrolysis, and the hydrogens can send it to Taiwan by different methods. And the most potential strategy is to transform the renewable energy into chemicals, and the chemical can stably send to Taiwan. To evaluate the feasibility of each supply chains, we carry out the process design with simulations, economic analysis, and life cycle assessments. And the reasonable assumptions are given to the transportations, electrolysis, and hydrogen fuel cells. And for the base case, the green electricity cost in the exporting country is fixed at $30 per megawatt hour. And the shipping distance is fixed at 10,000 kilometers, which is the distance between Taiwan and its major energy supplier. Let's take a look to the results. Although the electricity conversion rate is super high for the lithium batteries, the transportation of heavy batteries limits the charging capacity and leading to a ridiculous cost for the imported electricity cost. And it will face the same dilemma is transport the hydrogens using the metal hydrides. When transporting hydrogens after liquefaction, the coal energy can also send to Taiwan. And this energy can be recovered for power generation. In addition, the recovery of the compressed hydrogen can also bring some extra electricity to Taiwan. It should be mentioned that for safety considerations, the transportation of hydrogen to using the hydrogen vessels, which will making the cost become higher since most of the costs are paid for the transportation of the hydrogen vessel. And for the chemical supply chains, it encompasses the energy-extensive hydrogenation and dehydrogenation process. But the stable chemical can be transported using a large tank and leading to a lower imported electricity cost. In short, the imported electricity cost is the lowest when using the methyl cyclohexane supply chains. And furthermore, the life cycle assessment result shows that the supply chains proposed in our proposals can effectively reduce the global warming potential if compared to the fossil fuel supply chain. And the transportation distance is one of the important factors. When the distance is over 2,000 kilometers, the chemicals is one of the best solutions. And if the distance lower than 1,000 kilometers, we can choose compressed hydrogens. And for local storage, and lithium battery is ideal for daily use, and the compressed hydrogens for weekly and chemicals for monthly. To clarify the sensitivity of each factor to the supply chains, we will demonstrate the interactive dashboard at our display area. In conclusion, the lithium battery metal hydrides and hydrogens is not suitable for long-distance transport. And for the chemicals, methyl cyclohexane is the cheapest way to transport, but it requires more ship for transportations. And the methanol has the highest cost and global warming potential if compared to other chemicals, but it is the best choice for energy storage. In summary, the chemicals is suitable for long-distance transport and long-term energy storage. And the compressed hydrogens is suitable for short-distance transport and weekly storage, while the lithium battery is best for daily use. We are the team from National Taiwan University. Thank you for your listening.
Well, thank you so much, number 19. Now we are welcome the last team, number 20, for their presentation.
Good afternoon, everyone. I am Anuj from Team INTEL 20, and we come from Indian Institute of Technology, Bombay. Indian scientific system is based on 5 elements of nature. Heat, air, and water are 3 of the most vital for our existence. It is shocking to know that carbon dioxide emission from purifying water and space heating uses non-renewable fuels, which contribute to a staggering 45% of global CO2 emissions, which is 37 gigatons. In this context, how are we looking at a sustainable net zero future, particularly in these 4 UN SDGs? Can we generate thermal energy without any CO2 combustion or smoke? Yes. We can generate thermal energy directly from sunlight. Since this does not involve any CO2 combustion, we term this as green heat. Importantly, the sun provides us with 7,000 times more energy than what we consume today. How to harness this energy? The current solar thermal convergent devices or materials have an efficiency ranging from 40 to 60%. In this context, we present to you nanocarbon flow rates, a breakthrough in black body absorption with outstanding 90% solar thermal conversion efficiency. We term this as NCF. NCF mimics the unique floral arrangement of marigold flower. The morphology of NCF consists of nanoscale porous all-carbon NCF, which are isotropically arranged in 360 to give us NCF. This morphology drives 98% absorption of photon energy over the entire solar spectrum range from 250 nanometer to 2500 nanometer. Importantly, this is independent of angle. We combine chemical synthetic routes with engineering design principle to give us monodispersible and solution processable all-carbon NCF in a scalable fashion. What you see here are NCF coatings coated on metals, filter paper, and polymers. Even under intense light, they appear black, completely black, as you can see here. What happens to the light energy absorbed by this material? We must be wondering. So when NCF coatings are exposed to sunlight, they instantly reach a temperature of 150 degrees Celsius. This does not involve CO2, and hence we call this green heat generation by NCF coatings. Consequently, we know the exact amount of light energy falling on the NCF coatings. We can calculate the thermal energy output after excluding the radiative and convective losses. This gives us an outstanding performance of NCF at 89%. Now, why is this efficiency so high? We must all be wondering. So the answer to this lies in the internal structure of NCF. NCF consists of graphitically ordered domains in the short range, which goes on, and there's a disordering over the long range. This can be concluded from EXAF and Raman spectra. Now, such hard carbon structure property of NCF leads to strong phonon activation and activation in the short range domains, and intense phonon-phonon umclap scattering in the long range. This unique phenomena leads to phonon localization. Thus, any heat that is generated by NCF is trapped within it. And this leads to lower losses and consequently a higher efficiency, as we have seen earlier. This implies that any surface coated with NCF will reach a temperature of 150 degrees Celsius, as we see, compared to several carbon forms that we have: graphene, activated carbon, and carbon nanotubes. This high solar thermal conversion efficiency implies that even a weak light source, such as this laser pointer, can generate a temperature differential of 5 to 6 degrees Celsius, even on NCF coatings. We have done stability testing of NCF, which gives us a 5-year stable performance, accelerated testings. NCF generates green heat, which can be utilized for several applications. Two such functional prototypes that we are going to demonstrate to you today are called Sunspring and EcoWarm. Sunspring is an entirely solar-based water desalination unit, which gives us 4 times higher water output compared to solar stills, and with 25% energy reduction. We can achieve a net zero in 233 days compared to its market equivalent reverse osmosis technology. Similarly, EcoWarm gives us 5 times faster space heating with 20% energy savings and at a coefficient of performance of 0.99. Together, these two inventions can reduce carbon dioxide emissions by 40%, and with the higher efficiency of NCF considered, we can achieve a tangible shift in these 4 UN SDGs. And finally, we would like to thank you for this opportunity to present, and we are eager to demonstrate our prototypes at our demo booth. So please visit us. Thank you.
Thank you. Thank you very much. This is the last one. Thank you. At this moment, I would like to invite the judges to move on to the demonstration area, the booth. We will start from the number 17. So please right over this way, follow us. Okay. All the judges are present here. One more, hold on please.
Hello, you've heard our presentations, right? So, Drustanta is a Sao Paulo public library with net zero energy and net zero emission. Today, in our booth, we have the scripting method of our facade innovation, a 360 panoramic view of the interior building, and our architectural maquette that shows 5 different types of facades. Also, our HVAC systems and demonstration of our innovation tapered brick facade. Now, I want to ask the judges, which one will you choose for us to present first? Anything? Okay, so the 360 panoramic view, you can hold it like this. Sorry. Yeah, It shows that the inside of our building, there is the amphitheater public reading area, that is the evaporative cooling point in the inside that shows that the wind that could flow inside will be cooled by the evaporative cooling. So how do we maximize the cooling method by the tapered brick facade? Actually, this is our innovations. We want to demonstrate how the regular box brick facade will be shown in anemometer if there is wind sources like annual wind direction and direction in Sao Paulo. So as you can see, the result is very low. It's around 0.1 meter per second. But if we use our innovation tapered brick facade, as you can see, the result will become 1 meter per second. But how do we actually do this? We use this method by scripting in software named Grasshopper. So basically, in the script, we define the selected range of taper angle from 0 to 26.5, which is evaluated by one. Under indoor wind velocity result, if we use the regular box brick facade, is only 0.3, but if we use our effective facade, it will become like around 1 meter per second. So, yeah, this is the types of facade that is incorporated in our building. The first one is the canopy facade. And the second one is the vertical fin facade, and the third one is the curtain wall facade, and the fourth one is our solid facade, and the fifth one is our brick facade. So, HVAC system.
And for the HVAC system, we use indirect closed cooling ground source heat pump, which utilize earth constant temperature. As you can see here, we use two different refrigerant, which is still considered as natural refrigerant, and it has zero global warming potential. And we use ammonia for better heat transfer and water for ensure occupant safety while also maintaining their comfort. And by implementing this strategy, we can save energy consumption up to 23%.
So our design basically conclude to address three main problems, which is sufficient lighting, conserve energy, and avoiding excessive heat. With our design, as you can see in the conclusion, which is in this picture or at that poster, we achieve a net zero emission and net zero energy with a surplus 4% in summer. Thank you so much.
So what's the annual energy consumption per square meter? How many kilowatt hours?
For the annual energy consumption is 3.5 million a year. Per square meter is about 89. It's the best. It's the baseline, and after all of this strategy, we can reduce it up to 40.
So you are gold rated in ASHRAE? ASHRAE
Yeah, it complies
system.
with ASHRAE standard, yeah.
Okay.
So we can imagine the major carbon emission source in the library. One is lighting. Secondary is HVAC.
Yeah.
Third one is appliance. So my question is, how did you overcome those barriers? Do you know what the technology and any management systems you can solve the issue from your experience?
For the HVAC system and energy, it's powered by a solar panel, PV panel on the rooftop. And for the construction, we utilize local material for easiest transportation and reduce carbon emission.
Okay, yeah. Yeah. How long will the payback for your new facility, like underground pipeline and so on.
Okay,
Payback period.
So for the payback period, it's about 25 years, and
25 years.
yeah, and
Okay.
it's comply with the standard that has been set on the country as well. And for
Okay.
the overall price is $6 million, which
Okay.
is reduction of 60% than the baseline condition.
Okay, great. Thank you.
Okay.
Okay, thank you. The times, all right. Okay, judges, we're moving on to the next team, 18.
Thank you very much.
Test, check. Okay, thank you, judges and everyone. So we are coming from International 18. So what are we trying to do here? We are trying to implement green building also in the Sao Paulo, Brazil. But we are focusing on two kind of strategies, the passive and the active. Sometimes passive strategies are lack of intention. So we're trying to drive more about the passive. The first one is about terracotta panel facade. It's located in the market, the prototype in the red color. So it's actually a clay that going into the burning process. So it's trying to reduce solar radiation that coming to the building, so the cooling load inside the building will be lower. So the energy that we used to be cool will be lowered also. The second one is the fog catchers. We know that in the Sao Paulo, Brazil, same as Taiwan, it's hot and humid. The air contains water, of course. So how can we get benefits from it? The humid air that comes to the mass will catch the fog in forms of droplets and will be distributed into the piping system that will be reused again in the urinals, in the toilets for the building's water demands. And then we're having also the bromelated green walls. We're having the third facade. There is we put native plants into the facade to catch humid air, of course, to reduce water containment in the air, because our building is intended for public library. So it better to control the humid for stored books. And then you can explain, yeah.
And then to demonstrate how the fog catcher works, we use a 3D printed prototype where the actual mesh is made from stainless steel, and we use humidifier to show how the humid air passing through the fog catcher so the fog can be collected if it applied on the facade. This experiment revealed that the fog catcher can be applied to building facades to reduce humidity while collecting water for use. So this demonstration is representing the process of how the fog condenses and collects it into droplets that can be reused for the toilet and watering for the plant and green wall. And for the selected mesh collector, this is the prototype product for the design for the fog catcher facade. And the mesh collector is made of stainless steel, and the stainless steel mesh has a hydrophilic surface that on the front side that facilitates fog condensation that will directing the fog to the piping system, which is also influenced by its downward shape. So, this can easy to flow. Yeah. Additionally, the frame of the fog catcher is made of aluminum to making it easy to install.
Yeah, that's all.
Yeah, so I think this four innovative design is very, very impressive. I wonder if you have calculated the contribution to the lead calculation.
Yeah, we actually put.
How does that contribute, and what's your lead score based on your calculation of design?
So actually, yeah, based on our technologies and what are we trying to do, we have actually achieved in the silver score on the lead score. Yeah. But there's because it is a prototype, and I believe we're not trying to overconfidence and put it like a better score or whatever. We just make it like as same as our building and our technology.
Okay, great. Yeah, my question is, what is the payback period? For example, you have the fog catcher But actually, you needed a fan, right? Yeah, so you need electricity. So for the facility, you put here, what is the payback period? Thank you.
Actually, we actually calculated the payback period. It's around 5 years for the payback period. And 5 years. And I want to correct you a little bit because the fog catcher, it doesn't use electricity at all. So this is just a simulation. So the fog moves by itself. It doesn't use a fan.
But in the presentation, there is a fan.
Oh, it's for the experimentation of the, to testing the two different designs.
Okay.
Yeah, to visualize the designs.
Thanks.
Yeah, okay.
So can this design apply for the high-rise building?
Buat bangunan tinggi. It can be used for high-rise building.
Very expensive, I guess. Yeah, because all kinds of systems are costly.
About cost, I cannot be for sure, right? But actually, we use recyclable materials, right? So therefore, it actually cut the price also in the middle. So it's not really too expensive because we use reusable materials for almost all of our constructions.
Okay.
Yeah, especially the clay.
Okay, very impressive. Yeah.
Okay. Okay. Yeah.
All right. Okay. Thank you. Thank you, 18. All right, 19.
Good day to all judge. Our project is to design and estimate the feasibility of the energy supply chain. The supply chain will contain energy exporter and energy importer, and we want to transfer energy by the energy carrier. In our supply chain, we have assumed the parameters such as exporter electricity cost or the transportation distance. And in case this parameter will change with different situations, all the parameters in here can be freely adjusted by yourself. For example, if we want to increase the distance, then we can click this button to increase it. So all the simulation results will verify with this. And here we present the conversion, imported electricity unit cost, hydrogen unit cost, and the carbon emission. And if we want to know how much we should spend on this supply chain, the result will show in here. In here, we assume the target electricity in the importer is 60 terawatt-hour per year, which is average transported by 6 energy carrier. And the required electricity in the exporter is 164 terawatt-hour. So the overall cost right now is $17 billion. And if we only want to use these 3 chemicals as the energy carrier, then we can return them into zero and increase them. So under the same target electricity in the importer, the overall cost right now is $14 billion. As to the capacity and land area, they are shown in 3 different types: 100% solar, 100% wind, and the hybrid type. And the percentage between land can be tuned in here. So above is my brief introduction. Welcome to address all the parameters you want to know. Also, questions are welcome.
My question is you already switched the previous one. Yeah. Yeah, that one. Yeah. Usually, I think the cost will depend on the use size.
Yeah.
Okay. You should think about right here. You're talking about the hydrogen fuel cell or turbines, or maybe the conduction. The use hydrogen. You should think about the future. The energy system. It will affect the cost of the hydrogen import from the overseas.
Yeah.
So do you think do you determine according to this, or you just say you do not consider this?
I have considered it. For example, wait a minute. Can I next? Okay. For example, I am using the hydrogen supply chains, and this is the compressed hydrogen supply chains, and I compress the hydrogens and send it to Taiwan, and then I will send the hydrogens to the fuel cell, and the efficiency of the fuel cell is currently fixed at 55%, and this efficiency can be adjusted here.
But you just make an assumption, in the future, the hydrogen just for fuel cell, but maybe for the power generation,
Yeah.
it will total difference.
Yeah.
According to your analysis.
Yeah, I know. Because we are doing the comparison of multi-supply chains. So we are now fix the same basis for every supply chains and make the same. Yeah. Yeah, sure. Thank you. Because we have another work doing the methanol as combustion fuel. Yeah.
I think after your study, we know that transportation actually accounts for a good proportion in CO2. So the best way actually is to carbon trade instead of you bring everything back to Taiwan. You just buy it or sell it as a CO2 equivalent. Then you don't have to do any transportation. There'll be no transportation cost. Yeah.
Can you give us shorter questions?
Like my recommendation is to use on the spot the energy. Like if you say a carbon capture with hydrogen generation, right? You just use the hydrogen to generate electricity there.
Yes.
So it's a green electricity, so there's a carbon reduction. So you just take that carbon reduction. You don't have to make any transportation.
This strategy is based on Taiwan. Taiwan is lack of renewable energy, so we have to import from the energy-rich regions to Taiwan. So I just import from Australia to Taiwan. Yeah. I don't.
No question? One here. Thank you, 19, ladies and gentlemen. Last but not least, 20.
Hello everyone, I'm Nikita. Welcome to the demonstration section of Team INTL 20. Today I'm very excited to showcase our material, nanocarbon fluorides. As you have seen in our presentation, nanocarbon fluorides have high solar to thermal efficiency of 90%. Let me demonstrate this. What we have here is a filter paper coated with NCF. We will shine this filter paper with laser light, and instant light to heat conversion can be seen through this thermal camera. And an increase of 20 degrees can be seen, and that's within few seconds. We have used this principle because this material that we invented, we have realized it into a real-time application. This is our device. We call it EcoWarm. It is a solar-based space heating device. EcoWarm has been inside the EcoWarm, there is a low-powered electric bulb which gets heated up, which is used for heating of the NCF. That is our material, which is scalable. So inside this EcoWarm, we have copper plates onto which NCF is coated. When NCF converts the light to heat, cold air that is coming from here comes in contact with the heated NCF surface, and exiting air is hot, as you can feel here, and also can be seen from the thermocouple. We have field-tested NCF in harsh conditions of -8 degrees Celsius, where we could go from in a room that was the 4 times size of this particular room. And we could go from -8 degrees Celsius to 17 degrees Celsius temperature just within 20 minutes. EcoWarm, as compared to the existing technologies, is 5 times faster and saves 80% of energy. We have further extended EcoWarm space heating for drying of clothes. I'm pretty sure nobody in Taiwan likes damp clothes. So this same technology can be used for drying of clothes over here, where the person utilizing this dryer will be consuming 50% less energy as compared to what is available in the market. And individually, you all are contributing for the reduction of carbon dioxide emission. Additionally, we have realized we have used the NCF technology for solar-based water desalination and purification. What you see here is a unit we call Sunspring. The NCF material is coated on the top sheet, which covers the pipes through which we transfer heat transfer fluid. NCF converts the light to heat. That heat is carried by the heat transfer unit, fluid, and is taken to this chamber which has saline water. water gets heated, evaporates, and the water distillate is collected in the downside chamber, which is free from impurities. The one important thing about our unit is it consumes only 1 watt of energy for production of 1 liter of pure water, whereas the RO that most of us use consume 5 watt of energy for production of 1 liter of water. According to our conservative estimates, it will take, for our system, it will take 233 days to reach the net zero carbon period as compared to the existing RO technology. And I think that is very important because this technology is sustainable and cost effective, and especially for the countries which are economically challenged. Together, we believe that with our devices, we can pave way for the net zero. And isn't that why we all are here today? I thank you for your attention, and the flyer that is given to you has all our scientific publications and patents, and my team will be happy to answer any of your questions. Thank you.
Using this as the insulator, I think is one thing, right? As an insulator. Use it as an energy reservoir is a different thing. So what do you think your material is capable of? Energy reservoir or heat insulation?
So it's a material which acts as a conversion. It's a medium through which we, for example, let's say if we consider light as a currency, so it converts the light currency into heat currency, and we can use the heat to heat up the water and get purified water. Does that answer?
How much you can store?
So it's not a storage device, it's a convergent device. So it instantaneously converts and passes on to a substrate or a transfer material.
Yeah. And that's why we circulate the heat, we use the heat transfer fluid.
I'm more concerned about the stable of the material. According to your result, you say it can be reached over 6 years or 5 years. But according to your experimental result, just only maybe 16 hours. Okay, because in the future application, the durability or lifetime of the material is, I think, is the major issue of the application of this material.
So we have done accelerated lifetime testing of this material. So we have found that it has a lifetime and it can give a stable performance up to 8 years, but conservatively we say 5 years. And one of our PhD students has also worked for 5 years with this material.
But does it depend on the temperature? Your application temperature?
Yeah. There is a degradation, but the degradation is less than 5%. We have marked up to 5 years. Yeah. Yes.
Any questions?
I guess the water quality should be super good, right? Because this is distilled water.
Yes.
Okay.
Yeah, without any minerals.
For any purposes.
Yes.
What is the cost of NCF? Yeah.
It's so the cost of this material is $4 per gram, and with 1 gram we can cover like 1 meter square. And this with this amount of material we can cover like 5 times of this area, which is roughly 10 meters square. This much. That gives, and this is roughly 30,000 USD. Sorry, 3,000 USD.
3,000
NTD. 3,000 NTD. Yeah. Sorry.
Thank you. All right. Thank you very much for Team 20. We just completed all the demonstration and explanation. So, ladies and gentlemen, all the judges, now's your time to be escorted to the judging room. We are going to have a very intensive discussion about the results of the competition in international category. Thank you very much. 谢谢我们国际赛的评审们，你们辛苦了。现在呢，就是我们带领各位到我们评审休息室进行最后的总结和讨论。谢谢你们。All right, all the teams of the international division category, we just complete our entire morning and afternoon session. There are 20 presenting your brief, your PPT on the stage. Current time is 2:42, so you have a long hour to take a break. So at the 3:30, we are gonna to hold the closing and awarding ceremony. Again, at 3:30, I will going to invite you come back to the audience area to witness and join this moment of the truth. There will be announcements for your final result. So thank you very much. Taking this opportunity, I encourage you to don't forget to vote for the Best Popularity Award. There are 6 tickets you will get, and put all of your favorite team and the project into the box. And you will be one of the lucky individuals to win the one single big prize. And at the same time, you can have a drink, beverage, refreshment, and interact with your friends. Go to the different booths to exchange the business card or by any social media, and the social media to make a further contact to increase your friendship with the other countries. So once again, at the 3:50 afternoon, 3:30, will be the closing and awarding ceremony. So let's see your time, see your moment. Thank you very much. 谢谢各位参与，我们在3:30会进行闭幕以及颁奖典礼。谢谢大家。